Alrighty, folks, so we will now get into the third and final lesson of Chapter 9. And believe it or not, that is also the final lesson of Unit A. Unit A is just one chapter, Chapter 9, okay? So in this lesson, we're going to look at conservation of momentum in 2 dimensions. In the previous lesson, we did it in 1 dimension, okay? It's actually nothing new in terms of like physics concepts or anything here. We're just going to take what we were doing in the previous lesson and extend it into, okay, but what if the objects are not moving perfectly in one axis, right? Instead of being perfectly, left, right, for example, maybe it's a little bit up and right or down and left or something like that, right? So it'll be really all skills that we already have. We're just kind of putting them together here now for momentum because we've done 2D vector analysis in Physics 20. We've done conservation of momentum now in Physics 30. So just kind of putting those 2 skill sets together to analyze collisions in 2 dimensions and see how momentum is conserved. All right, so remember, momentum is a vector, right? So that means, like from vectors in Physics 20, it can have horizontal and vertical components, what we often call X and Y components, right? Side to side and up, down, or, west, east, north, south, that kind of thing. Okay, so far, like we've just been working in 1 dimension. So it's not that it didn't have these vector components. It's just one of these components has been 0, right? The car was driving straight east when it ran into the truck and then they both moved east together, right? That's just in 1 axis. That would just be in our X axis. So it's not that, we didn't have to think about components there. It's just that, well, the Y component in that situation was 0, so we didn't really need to bring it up, right? All we're going to do now is have situations where, well, there's actually momentum horizontally and vertically at the same time, okay? So just, for example, if this ball here is kind of moving at some angle, not perfectly to the right, not perfectly upward, but it's moving at an angle somewhere between up and right, right? It's directed at some angle up and right, then its momentum has a x component, which we would kind of think of as like the rightness. That's not a proper scientific term or anything, right? But it's the rightness of the ball's momentum. And a y component as well. That's the upness of the momentum. And we can show that like this, right? If it's got a momentum that's at an angle like this, okay, that means it does have this much momentum to the right here. Notice that's just like the horizontal length of the momentum vector. And it does have this y component, this vertical. It has this much up momentum as well. Notice that's just like the upness of this momentum. So we kind of got an uppy righty momentum, right? The x component is just saying the righty part, and the y component is just saying the uppy part, right? Notice it's just the vertical length of the momentum vector is the y component. The horizontal length of the momentum vector is what we call the x component. And if we knew the angle at which the momentum was directed, so if someone told us that, this momentum is at an angle of, let's say, 40 degrees from the horizontal, right? That's how it would be worded. If they told us over here, from the horizontal, it makes an angle of 40 degrees, right? Well, then look, we could just use our SOHCAHTOA, our trigonometry, right? If we knew the momentum, we could figure out its y component, we could figure out its x component, like we've always done when dealing with vectors in 2 dimensions. Right, so I mean, in Physics 20, we've done this with displacements. If you go for a walk, not perfectly north, not perfectly east, but, off at some angle north of east or east of north, right? We know that we can split that into the components and say, okay, well, you walked that far east and that far north. Do you see the 2 kind of sides of the triangle there, right? And we can do this, obviously, it doesn't just have to be north and east. We could think about walking west and north, right? Our x component would be like the westness of our walk. If we walked at an angle like that, how far did we actually walk west, right? Or south and west, or south and east. And we did that for displacements, then we did it for velocities, right? And it was the exact same idea. If your velocity is off at an angle, maybe you're moving 10 meters per second at some angle to the southeast, right? Well, how fast are you moving just to the east then? That's the x component. How fast are you moving just to the south then? That's the y component, right? Then we did it with forces. If you push something at an angle like that, how hard are you pushing it just to the west? That's the x component of that force. How hard are you pushing it just south, right? That's the y component of that force. All we're doing now, nothing new. We're taking that concept and applying it to a new vector that we've been talking about, and that's the idea of momentum. So if something has a momentum at an angle like that, it has an x component to its momentum. That's how much momentum it has just to the west or the left or whatever our x direction is there, right? And it has a y component. That's how much momentum it has north or up or whatever we're calling that y direction there. And so the kicker is now we can take our knowledge of 2D vector analysis and combine it with our knowledge of the fact that momentum is always conserved and say that, well, okay, if it's going to be conserved, it needs to be conserved in each axis individually as well, right? How could total momentum be conserved if it had some horizontal momentum before and it has a different amount of horizontal momentum now, right? That would mean the momentum changed. It wasn't conserved. Same goes for the vertical, right? If momentum, which is a vector, is going to be conserved, meaning it's the same before as after in both magnitude and direction, well, that means its x component before and its x component after need to be the same. And its total y component before and its total y component after need to be the same. Otherwise, it couldn't be the same vector with the same magnitude in the same direction, right? And so we can use that. We can say, all right, well, for momentum to be conserved, the total initial momentum in the x-axis needs to be the same as the total final momentum in the x-axis for all objects together. Again, individually, the object's x momentum might change, right? Just like in the previous lesson, individually the object's momentum might have changed, but overall the total momentum in the system, if it's an isolated system, will remain constant. Okay, so now we're just taking that and thinking about it in each axis individually, right? I love this picture. This is one of my favorite pictures of all time, right? It does such a good job of showing the law of conservation of momentum in 2 dimensions. They even use the same colors I always use for color coding. Red for Y, blue for X. Look, right? So look, this water is being shot out of this syringe here straight downwards. So water has mass, right? And here it has velocity, so it has momentum. Which way? Downward, right? This is a all y-axis momentum. It's straight down, right? It has no x component. This one is being shot straight to the left, the blue one here. So water has mass. This has velocity to the left. So this blue water has momentum to the left. And then look at what happens when they combine, right? When they collide each other. So the water particles here are colliding with the water particles here. And the total momentum is still conserved because now look at the momentum of this purple water where red has met blue, right? Downward momentum was here in the system initially. Leftward momentum was here in the system initially. Now that they've combined together, they kind of stuck together almost, right? And they're moving as one system here, right? I mean, it's a little more complicated than that because it's not really one object. It's like a bunch of particles of water, right? But you know, same idea, it's just happening for millions of particles of water. Look at their momentum. It's down and to the left, preserving the downward momentum that was in our system and the leftward momentum that was in our system. If we look at this purple stream here, right, what would be the x component of this momentum? Well, like that. That's P final x, right? And the y component, down, like that. Cool. I love that picture. It's such a good visual of the law of conservation of momentum in 2D, okay? So let's just take a look at conservation of momentum in 2D first before we jump into the math and the examples here. Let's just mess around with a simulation a little bit. All right, so here I've got 2 balls. Right now, time is paused, okay? But the pink ball is moving down towards the bottom of the screen, and the blue ball is moving to the right of the screen, okay? So if we think about the law of conservation of momentum, we know that the total momentum initially will equal the total momentum finally, in both magnitude and direction, right? So if we think about what our total momentum would look like right now, okay, we've got momentum to the right and momentum to the downward, right? And if we were to add those two, we know, okay, so overall the total momentum in this system is kind of downy righty, right? Its x component is to the right, its y component is downward. In fact, if you look in the bottom right of the screen here, I don't have a pointer I can use when I'm in this app, but you see the momenta diagram in the bottom right of your screen there. Notice they've just drawn a vector addition diagram for the momentum, right? They've added up momentum 1 to the right and momentum 2, they've added tip to tail, and then they've drawn the total momentum vector from the beginning to the end, right? How we always draw a vector addition diagram. Add up the component vectors tip to tail, and then the resultant or the total or the net is from where you started your diagram to where you finished. So sure enough, the total momentum is kind of down and to the right. Now, what will the final momentum look like? Well, without even thinking about it, the law of conservation of momentum tells us that it will be the same, right? The total momentum will also be down and to the right, and it will be the same magnitude. Okay, now individually their momentum might change, but the total must stay constant. The law of conservation of momentum, right? Not the friendly suggestion of conservation of momentum, the law. So let's just play this and see what it looks like. Here we go. Let's let these balls collide. Boom. Okay, let's see that again. Now, watch it one more time. We've got righty-downy momentum, total, and then they collide, right? And yes, individually their momenta changed, but the total momentum is still down and to the right. Look again at the momenta diagram here, right? They still add to give us that same net momentum vector. I'm going to replay it again, but now instead of watching the balls actually collide, keep your eye on the momentum diagram in the bottom right of your screen, okay? Watch that. Watch that. See? Right? The net momentum, the total momentum in the system didn't change. Okay? So they've collided, but in such a way to preserve total momentum, which will always happen because it's a law of nature that momentum is conserved in these collisions. All right, so I've set up another one here where they're going to collide. Now, in this one, the initial momentum in the system, it looks like it's entirely in the x-axis, right? We have a blue ball moving to the right, so its momentum is to the right, and a pink ball moving to the left, so its momentum is to the left. Now, those momenta work against each other a little bit and make it so that the total momentum in the system is a little bit smaller than it would be, you know, if they were both in the same direction. They're working against each other here. However, what I want to point out is there any y momentum in the system initially? No, right? There's no total y momentum, right? Everything's moving horizontally. So what does that mean final for the y momentum in the system? It's also going to be 0, right? Otherwise, momentum wouldn't be conserved. If suddenly there was some y momentum, it can't be the same momentum we started with, right? So let's just see what that looks like here, because I've got them set up so that they're not hitting each other perfectly dead center. They're going to kind of hit each other with a glancing blow. All right, now look at that. Okay, now sometimes students will say to me, hey, they're both moving vertically, so how could momentum have been conserved, right? Well, they are both moving vertically, but in opposite directions, so that they end up canceling each other's vertical momentum out, right? If you take a look once again at the momentum diagram in the bottom right of your screen, notice adding their two momenta is still giving us a total momentum that's entirely in the x-axis. Let's try that one more time. I'm going to try to make it even more of a glancing blow. Ooh, are they even going to hit each other? Shift it up a little bit. Here. Okay. See that, right? So yeah, they're both moving vertically now, but in opposite vertical directions. One's momentum is up, one's momentum is down. And we know that the y momentum of ball 1 has to be the exact same size as the y momentum of ball 2, but in the opposite direction. You know, just to throw some numbers in so we can think about it, maybe ball 1's y momentum is positive 10 kilogram meters per second, and ball 2's y momentum is negative 10 kilogram meters per second. So that when we add up their total y momentum final, it gives us 0 again, right? Positive 10 plus negative 10 is 0. That has to be the case because we know initially there was no y momentum in the system. And again, if you watch the momentum diagram in the bottom right there, you'll see that the total momentum vector, the net momentum vector, doesn't change after the collision. The individual momenta of the two objects does, but the total in the system stays the same. Okay, let's try another one. So now I've changed it so that the balls aren't bouncy, they're very sticky. So this is gonna be a hit and stick collision now, okay? So look, the two balls are merging kind of towards each other, right? So ball 1 and ball 2, they both do have X momentum, they both do have Y momentum, but notice their X momentum, it looks like the X's are canceling each other out, right? As much momentum ball 1 has to the right, ball 2 has, but to the left. So if we were to add those two X components together, tip to tail, we'd get no X momentum at all, right? Now their Y momentum, they both have Y momentum, and it looks like both of them are upwards, right? So in the beginning here, we do have Y momentum. It's the sum of ball 1's Y momentum and ball 2's Y momentum, right? It's vertical momentum. Okay, but the X momentum, it seems like they're canceling each other out. So the total X momentum here is 0. So now the balls are going to stick together. Let's see what that looks like. Here we go. Right? So look, initially we have some Y momentum, but no X momentum. Finally, we have some Y momentum, but no X momentum. Once again, keep your eye on that momentum diagram in the bottom right of your screen, right? Ball 1, uppy righty. Ball 2, uppy lefty. Okay, so that when they're just one object moving together now, their momentum is just up. Total initial X momentum 0, total final momentum 0. Total initial Y momentum, some number upwards. Total final Y momentum, some number upwards. Isn't that cool? Here's the same situation if they don't stick together, okay? So their X momenta initially cancel each other out. In this case, they don't stick, they bounce off each other, right? But look, now their X momenta still cancel each other out, right? Ball 1 was initially righty for its X component. Ball 2 was lefty for its X component. Then afterwards, ball 1's X component of its momentum is to the left. Ball 2's X component of momentum is just as large, but to the right, canceling each other out, giving us no total horizontal momentum, right? I mean, we can even put 3 balls in here. And if you watch just the momentum diagram at the bottom right of your screen, you'll see that the total never changes, even though all of these collisions are happening, right? Even though all of these collisions happen, the total momentum never actually changes. Isn't that cool? All right. So like I said, the procedure for analysis here is the exact same as what we were doing in the previous lesson and the exact same as what we did in Physics 20 for 2D, right? Just kind of putting those ideas together. So what do we always do, right? Whenever we have a vector that has components in both axes, so it has both an X and a Y component, we know that we can only add X components to X components algebraically and Y components to Y components, right? Walking east doesn't undo how far you've walked north, right? Only walking south can undo how far you've walked north, right? So X's can only really be added to X's, Y's can only really be added to Y's, right? So that's why if we're going to add them all up, well, first we have to separate them all into their X and Y components with trig, right? With SOHCAHTOA, okay? And then we just do a conservation of momentum calculation in each axis separately. So it's a lot like what we're doing in the last lesson. We're just going to do it twice, once for the x-axis, once for the y-axis. So that means we're going to say, well, momentum is conserved. So total initial momentum in the x-axis equals total final momentum in the x-axis, right? And solve for anything we don't know in the x-axis based on that equation. So what that means, right, we're adding up, just like before, we added up all the momenta of every object. Now we're just going to do that twice. We're going to add up the x component of the momenta of every object, okay, and say that's equal to adding up the x components for every momentum of the momentum of every object after the collision, right? Add up the x components of each object in the system's momentum initially, and then do the same for final, knowing that the results must be equal, just like we were doing before. Then do all of the same idea with the y components, right? And after doing that, I mean, every problem's a little bit different in terms of what we're looking for, but we might have the x component of something we're looking for. Maybe it's the final velocity of one of the objects. So we know the x component of its final velocity. We know the y component of its final velocity, right? Just to think about this example, maybe we know afterwards, horizontally, it would have to be moving that fast for momentum to be conserved in the x-axis, and vertically, it would need to be moving that fast for momentum to be conserved in the y-axis. So we can put those back together now to figure out what the actual v final is, right? By taking its x component and its y component. And hey, you got two sides of a right angle triangle, right? That's a vector addition diagram for us with the component vectors, the components of the vector here, right? So if you know this side and you know this side, you found them with conservation of momentum in each axis, you can find this side with the Pythagorean theorem, right? This squared will equal this squared plus this squared, right? That's just the good old Pythagorean theorem. C squared equals A squared plus B squared. Okay, so that will give us that final velocity. And then with SOHCAHTOA, we could get the direction as well, right? The direction will be an angle. Remember, it's not just good enough to say northeast or uppy righty. We got to be more specific and actually say at what angle. But we'll have all sides of this triangle. To get that angle, we could just use that tan is opposite over adjacent, right? Inverse tan of theta, inverse tan of y component over x component, for example, would give us this angle, right? This is just one I made up to kind of refresh your brain on how this stuff works, but that's the idea. We're going to apply conservation of momentum in the y-axis, maybe to find a final y velocity, right? Conservation of momentum in the x-axis to maybe find a final x velocity, and then Pythagorean theorem to get the overall final velocity, and SOHCAHTOA to get its direction. Okay. Now, it's not always that we're going to be looking for a final velocity. We might be looking for an initial velocity, or we might just want to find an angle or something like that, right? Or a final momentum, okay? But just, that's generally the procedure, right? Something like that. We're going to be able to use conservation of momentum in the x-axis and in the y-axis to find unknown quantities, okay? So, just a reminder of the additions. So again, remember, if we've got two objects, let's say, and they each have a momentum and maybe both have momenta in both axes, right? So you can see both of these have a momentum in the x-axis and in the y-axis, right? Well, again, we can add those up tip to tail. So if we wanted to represent this with a vector addition diagram, tip to tail means the tip of that one is going to go on the tail of that vector, right? Tip to tail, where one ends, the next one starts. Okay, and then to get the resultant, the total momentum, we go from the beginning of the first to the end of the last, right? Tail of the first to tip of the last, from where we started the diagram to where we ended up. So I'm going to add in the sum vector here. There it is, right? That is the total momentum in our system. Okay, that's the total momentum in our system. It's just the result of adding those two vectors together. Okay, and notice, no matter where, I can mess around with this, it's always the same idea. Okay, so what we're now doing, though, is we're trying to figure out maybe what we're trying to do is what is that total momentum, okay? And it always just comes from, well, that total momentum also has an x component. What is its x component? Well, it's the x component of the first vector plus the x component of the second vector. So if I add in the components here, right, I know that looks like a lot. I'm just going to move this off to the side for a second, okay? But look, this vector here that I'm moving now, it's got an x component. Unsurprisingly, it's to the left, right? This vector here, it's got a x component. It's to the right. Now, if individually I just add up their x components, so I'm just looking at this x component here, I'm going to add it tip to tail to the x component of the other vector. Okay, I'm just going to offset them a bit so we can actually see them. Now look, those two x components together, they've been added tip to tail. Let's take our result vector, our total momentum, and look at that, right? It fits perfectly. It's drawn, it's the size of taking that leftward momentum from the vector they've labeled A, canceling out a bit with the rightward momentum from the vector they've labeled B, and what we're left with is just the x component of our total vector. Well, that makes sense, right? That's the total vector. It's the result of adding them. So individually, it's also the result of its x component is the result of adding the x component of each vector, right? And you can probably guess we could do the same for the y components. So again, this is our vector, right? Vector b is up and to the left, meaning that its x component is to the left, and now look at its y component. It's upward, right? If I add tip to tail the y component of the vector they've labeled a, look what that's going to give us. It's going to give us the y component of the total vector, right? See that? See how perfectly the y component of the total lines up with this one, right? So again, same idea. The total y momentum of our overall net momentum in the system just comes from adding the y momentum of one object's momentum and the y component of the other object's momentum. That gives us the total y momentum in the system. Same thing we did in Physics 20 with forces, displacements, velocities. It's just a new type of vector that we didn't talk about in Physics 20, momentum. Okay, so we'll get into an example in just a second here, but first I just want to pause and because we've now circled back to, remember in the previous lesson when I talked about how, when can we use momentum and when can we use conservation of energy, right? And we said that energy can be a bit quicker and easier. And I said you might not be getting it now. You might not be seeing now why energy can be easier. After we've done a couple of these, you might see why. Because I won't sugarcoat it. While the concepts are simple, right? I mean, it's just conservation of momentum and some trigonometry, right? The actual solving process can get long. It's not like incredibly difficult or anything in terms of the math and the process you're doing, but it can take a while because we're going to have to separate everything into X and everything into Y. So this is what I was referring to when I said conservation of energy can be quicker than conservation of momentum if we can get away with conservation of energy. Remember, we often can't get away with conservation of energy because energy is better at leaving the system. It can be harder to keep track of, and we don't have equations for a lot of types of energy, like thermal or chemical and all that kind of stuff, right? So why don't we have to worry about all this? Why, if we're allowed to use conservation of energy in a certain example, why don't we have to worry about all this X and Y stuff? Because sometimes students say, well, do I have to find the X component or the Y component of the kinetic energy? Well, no, we don't, because energy is a scalar, remember, right? Which means it doesn't have an X component or a Y component. It doesn't have a direction at all, right? Drawing an energy vector doesn't even make sense because energy doesn't have a direction. It's not a vector, right? There's no such thing as the eastness of the energy or the northness of the energy, right? Energy has no direction. So we don't have to do all this stuff with splitting it up into its X and Y components. Right? So no need to separate it, give signs, opposite signs, giving opposite directions, all that stuff doesn't even make sense for energy because it doesn't have a direction at all, much less X or Y components, right? Energy is conserved in magnitude, but that's it because that's all there is to energy, just a magnitude, no direction. It's a scalar. All right, let's try out our first two-dimensional conservation of energy question. Of momentum, not conservation of energy. Won't work for this one as we'll see when we read it. Okay, so a 900 kilogram police car was moving north. So north, okay, let's think about that. That's perfectly in the y-axis, right? At 50 kilometers per hour, which was the speed limit. It was hit by a 1,200 kilogram truck moving east. Okay, so our truck was moving straight east. So this one's kind of nice because yes, there's momentum in both axes, but individually each object is only y or only x. We don't have to split this velocity into its x component because we can see that its x component is 0, right? It wasn't moving west or east, just north. So all y, no x. And then vice versa for the truck, all x, no y. That won't always be the case, but we'll deal with those when they come. So right after the collision, the vehicles were intertwined. So could we say that total kinetic energy will equal total final kinetic energy here? No, right? Because this is an inelastic collision. They stuck together. So total energy might have been conserved, but remember, in a hit and stick collision, it's impossible for kinetic energy to be conserved. This is an inelastic collision. So we won't be able to say that total initial kinetic equals total final kinetic. Remember, even if it were a hit and bounce, there's a good chance it's still not elastic, but we definitely know it's not elastic if they stuck together. Anyway, afterwards, they're intertwined, moving together at 40 kilometers per hour, 58 degrees east of north. Remember, when they're written like that, that means east of north. If it were like this, it would be north of east. Reminder that those are different things. East of north and north of east. 58 degrees east of north is different than 58 degrees north of east. We'll talk about what that means in a second. And it asks, was the truck driver speeding? Okay, so what do we need to figure out to answer that question? Was the truck driver speeding? Well, we need to figure out what was the truck driver's velocity before the collision, right? So we're looking for V, I'm going to call it V truck initial. Okay, V T initial, T for truck. That's what we need to find. That's the purpose of this question. So let's just get our bearings a bit here. I highly recommend, in fact, it's kind of even considered part of a full solution, draw your before and after diagrams, right? It can be a little hard to parse out all this information, but putting it into a diagram can help you get a better idea of what's actually going on. And then especially a vector addition diagram, once we've got our bearings, super helpful for these, okay? So before, we had a 900 kilogram police car that was moving north. I'm just going to simplify the car down to a box, okay? We're looking at it from above. And a truck that was moving east. So I'm going to draw the truck as a box, okay? Now, the police car, we know was moving north at 50 kilometers per hour. So I'm going to say velocity, I'm going to say P for police, okay? Initial is 50 kilometers per hour straight north, okay? And then the velocity of the truck, we know it's straight to the east, but we don't actually know what it is. That's the point of this question. Okay. Now, actually, before I even move on to my after, I'm just going to draw a quick vector addition diagram for the momentum in this system, right? The total momentum in this system. So a vector addition diagram for momentum. Not for velocity. I mean, we could draw one for velocity, but there's no law of conservation of velocity, right? So that's why I'm thinking about momentum here. So what would the total momentum in this system look like? Well, we've got the police car's momentum. That's straight to the north. So that's going to look, something like this. This is the momentum from the police car initial, okay? Now, tip to tail, if I add that to the momentum from the truck initial, right? So tip to tail, we know it's straight to the east. That's the momentum from the truck initially. What's the net momentum in our system? Well, to draw the resultant vector, right? We always go from where we started, there, to where we finished our diagram, there. So unsurprisingly, the total momentum in the system is at some angle north of east, or in this case, the way I drew it, east of north, right? So this is the total momentum in the system. Well, that makes sense. If you add a northward momentum to an eastward momentum, you get a momentum that's partially north and partially east, right? So this is our total momentum initial. And we can kind of see its y component is actually just the initial momentum of the police car. That makes sense because it was the only object with y momentum to start with. And its x component is just the truck's initial momentum. That makes sense because the truck was the only thing with x initial momentum, right? The police car wasn't moving west or east, and the truck wasn't moving north or south. All x, no y, all y, no x. Okay, so now after, it tells us the two vehicles are intertwined, so they're kind of stuck together as one object. Something like that, right? Moving together at 40 kilometers per hour, 58 degrees east of north. So before we do anything there, our first step is to figure out, well, what the heck is 58 degrees east of north, right? What does that mean again? Because then we can't really draw it until we know what it's saying. So it's saying that their velocity is pointed 58 degrees east of north. So that means from north, we need to go 58 degrees of it, right? A common student mistake here would be to say 58 degrees there. They'd say that's 58 degrees and then draw their vector like that. That's not right because that is 58 degrees north of east, right? Starting from east, they went north of it, right? Think about it. If you start at your house and you walk north, you end up north of your house. You don't end up house of your north, right? So where you start from, we are going north of east, okay? So that's why that one's wrong. We wanted to go 58 degrees east of north. So let's try that again. We know we're somewhere in this quadrant though, right? We're somewhere between north and east. So we need to go 58 degrees. Obviously doesn't need to be perfect and break out the protractor or anything, but 58 degrees east of north. So that is what our velocity final looks like, right? It's somewhere, it's north of east, okay? Sorry, east of north. Okay, so that is our velocity of our, I'll say TP for truck police system, because they're really now they're one kind of final object, right? So V truck police system final is 40 kilometers per hour at an angle of 58 degrees east of north. Okay, now that velocity, it has both X and Y components. Right? It has, I'll draw it this way. Since they gave us the east of north angle, it makes a little more sense to probably draw it this way. Do you see that? That's the Y component. That's the northness of the final velocity. That's V truck police final. Okay. This is the X component. V truck police final X. Whoops, I forgot to put a Y here. That's the Y component. Right? So it's just saying if it's moving 40 kilometers per hour at that angle, right? Well, that means it's really moving this fast to the north and this fast to the east. It's just doing both of those things at the same time, right? Okay, now, without even having drawn that diagram, right? Pretend I just didn't even draw that, okay? We're going to go back in time to before I drew this. What's the final momentum in this system look like? What would the final momentum in this system look like? We know, without even thinking too hard about it, it has to look the same as this, right? Momentum is a quantity that is always conserved, right? So the total initial momentum looked like that. The total final momentum, we could just go copy and paste. It needs to look the same. Momentum is conserved. That's a fundamental law of the universe, okay? It's just that before, that momentum was in two different objects. Now they've hit each other and stuck together. So all of that momentum is still there, but it's just in this kind of one object, quote unquote, that is the truck and the police car stuck together. Okay, now that momentum final, you can see it also has a Y component, right? Can you visualize the Y component? It's the northness of this final momentum. So that is the total momentum final Y, right? And it also has an X component. That's the total momentum final X. And now we know that, again, this angle is 58 degrees and this angle is 58 degrees. So we can use trigonometry in SOHCAHTOA to find these components as needed, right? And if we need to find any of these components, we can do that as well, okay? So let's just start thinking about how we can actually solve this then. We know that all of the X momentum initially was in the truck, and we need to find its velocity, right? And we know that this initial X momentum has to be the same as this final X momentum. So let's just go ahead and start there. Remember what I said, right? I literally teach physics and I'm not sure exactly where we're headed in terms of a final equation, right? And you shouldn't try to be either, right? What you should do is apply the basic physics principles, right? So just applying physics principle number 4, the law of conservation of momentum, okay? I'm going to start out with a pretty basic idea. And that basic idea is that I know the total initial momentum in the x-axis will equal the total final momentum in the x-axis, okay? And now I'm going to say, all right, so what's the total initial momentum in the x-axis? Well, we've got two objects. We've got a truck and a police car. So the total x component of all the momentum will be the truck's initial x component plus the police car's initial x component. And you might be screaming at your computer screen right now saying the police car doesn't have any initial x momentum. You're right, it doesn't. We'll cross it out in a second here and say it's 0. But I'm just emphasizing the point that what is the total initial x momentum? It's the sum of every object's x component of its initial momentum, right? Some of them might be 0, that's okay. But the idea of what the total initial x momentum is always the same. Add up the x components for every object initially. And same goes for the final. What's the total final momentum? Well, final, we only have one object. So we only have one x momentum to think about. The momentum of the police truck, combination that we now have. Final, its x component, right? So all I've done there is apply the law of conservation of momentum, but using just the x components here. And again, that's because we can't add x's to y's. We can't add something with both x and y to something that's just x, but we can individually break them down into x's and add them up, and we can individually break them down into y's and add them up, right? The same way you can't add a north to an east by just adding the two numbers, right? But you can add a north to a north or a north to a south by just adding the two numbers. Okay. Now, just kind of taking stock of this a bit here, right? We know the truck's mass, okay, and we know the police car's mass. So afterwards, we know the total mass of the object. It's just those two masses added together. We also know its velocity, and we know the angle it was directed at. So we can find the x component of its velocity, and therefore, right, multiply that by its mass, and we've got the x component of its momentum. Okay, just a note here, be careful. A common student mistake would be to use SOHCAHTOA and find the x component of the velocity, which is great, but then they say that that must have been the truck's initial velocity. Do you see the problem with that though? There's no law of conservation of velocity, right? No one said the x velocity had to be the same after as it was before. The total x momentum needs to be the same after as it was before, right? So we can actually see it won't be the same velocity because the mass has changed, right? So if mass changed, velocity needed to change in order to keep momentum constant. Because again, momentum is just mass times velocity, right? Whoops, I forgot the equals. Momentum is just mass times velocity, right? So if the mass changed, which it kind of did now because instead of just being the truck moving in the x-axis, this larger mass is now moving partially in the x-axis, right? Well, the velocity needs to have changed as well then. Otherwise, how could momentum have stayed the same in the x-axis? Okay, so with that in mind, let's just keep going at this, all right? We'll get more clear on what we actually are knowing and what we need to figure out here. Okay, but we're on a good start here. The momentum of the truck initial in the x-axis, well, that should be able to let us find the velocity of the truck initial, because that's just its mass times its initial velocity, right? But you're right, the momentum of the police car initially in the x-axis is 0 because it's only moving north. So that simplifies our calculation a bit here, which means the momentum of the truck initial, its x component, is actually just the momentum of the whole system final in the x-axis, right? And look at this. This is the physics speaking to us through the math again here, right? Look what it's saying. All of the momentum in the system horizontally is saying just came from the truck's initial momentum. Well, yeah, that's totally true because the police car didn't give us any x momentum, right? So that checks out, okay? Now, what's the momentum of the truck initially in the x-axis? Well, it's the mass of the truck times its initial velocity's x component. Now for the truck, it's all x, no y. So we could call it v truck initial x, but really that's just v truck initial because it's all in the x-axis, right? It's not like it has an x component and a y component. It's all x component, no y component, okay? Now finally, different story. So what's the mass of the police truck system final? Well, it's the mass of the police car plus the mass of the truck, and its momentum will be that mass times the x component of its velocity, right? To get the x component of this momentum, we need to multiply by the x component of that velocity. So v truck police final x. Okay, so now this is where we realize, all right, well, we don't actually have the x component, but we do have the velocity overall, right? It's at 40 kilometers per hour at some angle east of north. So with our little diagram here, and this is what I always tell students, right? Sometimes I find students, they'll just draw the diagram and they'll say, all right, I drew my diagram, I'm done with that, right? The reason we ask you, or the reason like we encourage you, right, in the first place to draw the diagram is that you can keep coming back to it and it can keep helping you, right? Because then you get to this stage and you realize, oh no, I don't have this yet, right? We go back to our diagram and we see, aha, we can get that with some SOHCAHTOA, right? So remember, sine equals opposite over hypotenuse, cos equals adjacent over hypotenuse, tan equals opposite over adjacent, right? That is on your formula sheet if you've forgotten them, but we have this velocity, it's 40 kilometers per hour. So we have the hypotenuse of this triangle, right? And we want the x component, which is opposite to our angle. So opposite, hypotenuse, that sounds like a job for sine, right? So that means sine of 58 degrees equals opposite, which is what we're looking for, v, the x component of their combined velocity, right, over hypotenuse, which is just their actual total velocity. Okay, which means apply both sides by that combined velocity, and we'll be solving for the x component of their combined velocity, which is what we need to finish up our conservation of momentum calculation here. Okay, so I did that, multiplied both sides by their final velocity, okay? Gonna need to convert that 40 kilometers per hour into meters per second, so multiply by 1,000, because there's 1,000 meters in every kilometer, then divide by 3,600, because there's 3,600 seconds in an hour, and we just want meters per second, not kilometers per hour. What that gives you is 11.1111 meters per second, times the sine of 58 degrees, and we'll be finding the x component of their final velocity, which again, we can then use to find the x component of their final momentum. So this gave me 9.42276 meters per second, and that would be to the east, right? The overall velocity is between north and east, meaning the x component is just to the east. And there we go, right? So now let's just take stock of what we know. Mass of the truck, yes, we were given that, right? It's 1,200 kilograms. Velocity of the truck initial, that's what we wanted to find. Mass of the police car we were given, mass of the truck we were given. And now with just some SOHCAHTOA, we've got the x component of the velocity that they move together with after. Meaning that we have everything we need to figure out the one thing we don't know, the velocity of the truck initially. Okay, so don't get too bogged down like in the, like I know the equations for these can sometimes look a little bit intimidating, but all we're really doing here is applying the law of conservation of momentum, right? We're looking at this situation, we're saying, okay, this has some x momentum. Well, initially the truck was the only thing with x momentum. So that truck's x momentum must be the same x momentum that the system has afterwards. And since we know the mass of the system afterwards, and we know the mass of the truck, we can figure out what velocity it would have needed initially to have enough x momentum to give us what we have here, right? And we know it did because momentum is always conserved. Okay, so we're just about ready. We want to solve for the velocity of the truck initial because we want to know if the truck was speeding. Right now it's being multiplied by the mass of the truck. So divide both sides by mass truck. And before I put in my numbers, definitely, I really, realistically, I should have done this at the very beginning, but sometimes we forget. But now that we're about to put in the numbers, we definitely want to make sure we remember we're dealing with vectors, so we know opposite signs need to have opposite directions, right? I'm going to call east the positive x direction and west the negative x direction, and I'll call north the positive y and south the negative y. We actually probably would have gotten away with forgetting here, not that it's okay to forget, but we would have gotten away with it because we don't have multiple vectors in opposite directions. That definitely won't be always the case. So just keep in the back of your mind, whenever you're about to put in your numbers, make sure you haven't forgotten direction signs when it comes to vector analysis. Okay, but here we go. So that means since our x velocity was to the east, we'll make it positive when we put it in. So plugging in our numbers here now, the velocity of the truck initially must have been the combined mass of the truck and police car, times their final x velocity, which we found to be 9.42276, divided by the mass of the truck, which we know is 1,200 kilograms. And again, this kind of makes sense, right? Like looking at what we've got here, because we know this, our numerator, that's just the final x momentum, the final horizontal momentum in the system. And we know from the situation that all of the x momentum in the system came from the truck initially, right? So whatever the final x momentum is just the same as the truck's initial x momentum. So since momentum is mass times velocity, if we divide that x momentum by the mass of the truck, we should be left with its initial velocity. Okay, so going ahead and doing the calculation, I got that the velocity of the truck initially was 16.4898 meters per second. I got a positive, which is a good result because we defined positive as east, right? We made our x velocity here positive and it was east. So that means the velocity of our truck initially was to the east. That's a good sign because that's what we were expecting. The truck was moving to the east initially, okay? Now always be careful. Yes, we found what we needed to answer the question, but have we actually answered the question? Because the question is, was the truck driver speeding, right? Well, we know that the speed limit was 50 kilometers per hour, and now we know that the truck driver was going 16.5-ish meters per second. So we are close to being done, but we now need to figure out, okay, is this velocity in meters per second? Is it faster or slower or the same as 50 kilometers per hour, right? So we've got options. We could convert 50 kilometers per hour into meters per second and compare, or we could convert this into kilometers per hour and compare. I might do that one. So we're going to convert to kilometers per hour. So it takes 1,000 meters to make 1 kilometer, right? So we need to divide by 1,000 here. And we can check that our units are canceling out correctly. Yes, meters over meters will cancel out. And then we don't want to know how far they go in 1 second. We want to know how far they go in a whole hour. So we'll have to multiply by the 3,600 seconds there are in each hour. So we can double check again, seconds and then over seconds. So those cancel out. We're left with kilometers per hour. And I got that the truck was moving 59 kilometers per hour. So we're close, but the question wasn't how fast were they going, it's were they speeding? So our final answer is actually just going to be yes, they were speeding, right? 59 kilometers per hour is faster than 50, which was the speed limit. All right, so let's try out one from an old diploma here. So again, often nice with these to read the question first so we kind of know what we're looking for. So immediately before the collision, the momentum of the locomotive car system is okay. All right, so we're just looking for the total momentum before. So in a movie stunt, a car and a train locomotive intentionally crash. The collision is illustrated in the diagram below. All right, so we've got a train going east. We've got a car going north. Okay, again, that's kind of nice because now we don't have to take yes, there's X and Y components going on here, but for each individual object, we're not going to have to split their momentum up into X and Y components, right? This is all X, no Y. This is all Y, no X. So actually, this is one we can get pretty quick with just, we're not even being asked to do conservation of momentum here because we're just asked about before. So we know it'll be the same after, but we don't even need to go that far. So honestly, I think a vector addition diagram will do most of the work for us here. We've got the train. The train has momentum, obviously, to the east. Call that momentum train initial. And then we've got the car. The car's got momentum to the north. And just taking a second here to look at numbers, yes, the car is going, 2.5 times faster. It's going 25 meters per second, but look at the mass difference. This is 5 times 10 to the 4 kilograms or 50,000 kilograms. Well, this is just a little over 1,000 kilograms. So this has about 50 times the mass. This has about 1/50th the mass. So even though the velocity is 2.5 times bigger, that mass is going to make a lot bigger difference. So most of the momentum in this system is coming from the train. So I'm just going to draw that vector arrow a bit smaller because we know it has less momentum, okay? But it is to the north. Let's go ahead and draw a vector addition diagram and just see what we're working with. So the VAD, vector addition diagram, I'll add it tip to tail. Okay, I'm going to go ahead, again, just a reminder, you can draw it either way. So we could go first drawing the momentum of the train initial, and then tip to tail adding the momentum of the car initial, right? And then say, okay, so our total momentum initial would be from where we started our diagram to where we finished it, like that. That's our total initial momentum in the system. That's what we need to find, magnitude and direction, because momentum's a vector. But I just want to remind you again, because sometimes students get a little stressed out. They say, but what if I wanted to draw it like this? Would I still get the right answer? And you totally would. So if you added, we know it doesn't matter the order we add them, right? We should still get the same result. So if I drew the momentum of the car initial and then added tip to tail the momentum of the train initial, look, we still get the same total momentum. We get a momentum that's somewhere north of east, right? The only difference here is that with this setup here, when we go to find the angle, what probably makes the most sense to find is this angle, since that's how we drew our vector addition triangle, right? So we'll do opposite over adjacent and inverse tan of that to get that angle, right? Whereas doing it this way, you would probably find this angle. And it's still the right result. It's just this one would be north of east, whereas this one would be east of north. So maybe, this is 5 degrees north of east. This is 85 degrees east of north. Those are actually the same direction, right? If I were to go 5 degrees north of east, if that were the direction that the vector was pointed, it was aimed 5 degrees north of east, that's actually the same as aiming 85 degrees east of north, right? Because east and north make a 90-degree angle total. So just a little reminder there that the order you add them doesn't matter. It just means you might end up finding the east of north angle instead of the north of east angle. Okay. With that being said, just looking at the multiple choices here, they've got north of east in all of the options. So maybe we'll just go with that one just so we don't have to do that extra step at the end of doing 90 minus our angle. Okay. But here we go. Let's see if we can find that net momentum. And this isn't going to be too bad at all because the momentum of the train initial, the x side of this triangle here for the total momentum, right, is just its mass times its velocity, which we've got. Same thing here for the car, mass times velocity, we've got those. So we're very close to having these two sides of our VAD triangle. Once we've got those two, we just need to do the Pythagorean theorem to find the magnitude and then SOHCAHTOA to find the direction. So let's jump into it. Momentum of the train initial will be the mass of the train times its initial velocity, which is just 5 times 10 to the 4, or 50,000 kilograms, times 10 meters per second. And again, I'm going to call east the positive x direction, west the negative x direction, so I'll make that a positive 10 meters per second. And we get that the momentum of the train initial is 500,000 kilogram meters per second. All right. If we repeat for the car, we're basically there. We just got a Pythagorean and SOHCAHTOA for direction. So the momentum of the car initially will be its mass, 1.2 times 10 to the 3, or 1,200 kilograms, times, I'm going to call north the positive y direction, so positive 25 meters per second. And we get that the momentum of the car initially is 30,000 kilogram meters per second, north. This one was east. So just redrawing this with our known stuff there now, just didn't want to make it too crowded up there, right? Look, we're back in grade 10 math. We know this side of the triangle and this side of the triangle. We want the hypotenuse. So c squared equals a squared plus b squared, right? In this case, that means the total initial momentum squared is equal to the momentum of the train that we found to be 500,000 kilogram meters per second squared plus the momentum of the car that we found to be 30,000 kilogram meters per second squared. And therefore, the total magnitude of the initial momentum in the system, square root both sides. And so then when I square 500,000, square 30,000, add them together, and then square root, I'm getting 500,899 kilogram meters per second. So that's the total magnitude of the momentum in the system. Now to 3 significant digits, that would be 5.01, right? 1, 2, 3, 4, 5. 5.01 times 10 to the 5 kilogram meters per second. Okay, again, careful, that 0 gets rounded up to a 1 because it's followed by an 8. All right, so going back to our options here, we can eliminate C and D, right? And truth be told, if we think about this, we can actually also eliminate A without actually calculating the angle. We will calculate the angle just for the practice here. But to be honest, this doesn't make any sense. 68.2 degrees north of east, right? 68.2 degrees north of east. That means it's closer to north than it is to east, meaning that most of the momentum in the system is to the north, right? Meaning the y component is bigger than the x component. Well, that doesn't make any sense. We know the train has way more momentum than the car. So we can honestly eliminate A, right? B makes a lot more sense. It's only 3 degrees north of east. Not a very big angle, but the train to the east has way more momentum than the car to the north. So B makes sense. Let's just actually calculate the angle to make extra sure, but I'm feeling pretty good about B being the right answer. But now, right, we can come back to our diagram, see what I mean? It can keep helping us. How do we figure out what that angle is? What direction is this momentum actually pointed in? Well, we know this side, opposite. We know this side, adjacent. Technically, we know the hypotenuse too, but there was one more calculation involved in getting that. So it's one more step likely that we could have made a mistake. So I like to just use these. Plus, we typically have them drawn out nicely and added to our diagram anyway, so they're easy to see. So, well, opposite, right? We know opposite, we know adjacent, SOHCAHTOA. TOA. So it sounds like we want to use the tan of whatever that angle is equal to opposite over adjacent. So 30,000 over 500,000, right? And then remember, we don't want tan of theta, we want theta itself. So tan is an operation. We're taking the tangent of theta. So to undo that, we take the inverse tan of both sides, right? That is second tan on your calculator or shift tan on your calculator, depending on what you have. So second tan, inverse tan, or arctan we sometimes say, of 30,000 over 50,000. Sorry, over 500,000, not 50,000. And I got, when put that in my calculator, so I would have gone second or shift, second, and then tan, to get that theta is, sure enough, 3.43 degrees. Okay, make sure your calculator's in degree mode, not radian mode, especially if you've taken Math 30 recently. You might have your calculator in radians. It's possible. Okay, so 3.43 degrees, and sure enough, that is north of east, right? That angle is 3.43 degrees. Starting from east, we go 3.43 degrees north of it. Okay, so like we predicted, B is indeed correct. Again, if you had drawn your VAD the other way, if you had first done car, then train, you would be totally okay. What you would have gotten as your angle is 90 minus 33.43, which is 86.57 degrees, but yours is east of north, right? And you're right too. So when you looked at the options, you would realize, oh, okay, I just did east of north, so one of these must be the same as mine, just, the north of east way of saying the same thing, right? 86.57 degrees east of north is the exact same thing as 3.43 degrees north of east. That's 86.57, that's 3.43, okay? Obviously not to scale there, but there we go. So definitely the answer to that one is B. Okay, now it asks us, what type of collision was this? So type meaning elastic or inelastic. Well, you tell me. The two cars stuck together, right? So can kinetic energy be conserved if they stuck together? No, right? Because again, kinetic energy is mass times speed squared over 2. And when they stick together, they're kind of losing some speed, so to speak, right? And they're not making up for it by getting more mass. The easiest way to visualize that is, right? To think of like the extreme case where the two stick together. So again, since energy is a scalar, it can't add to cancel itself out. So right now there's a lot of kinetic energy, or at least both of them are contributing kinetic energy. But then when they stick together, they both get slowed down, right? Now momentum was still conserved because the momentum was canceling itself out a little bit, because momentum's a vector and it can do that, right? Opposite directions cancel each other out. But for scalar energy, that doesn't happen there, right? And so that's why when they stick together, kinetic energy can never be conserved, and therefore it is not an elastic collision. So it is an inelastic collision. And also just, you shouldn't take this for granted, but if we wanted to think about it realistically too, there would definitely be heat and sound energy and energy going into deforming the materials in the train and the car, right? And that right there tells us the kinetic energy would be lost from the system. It would leave as heat, sound. But again, don't take that for granted, okay? Sometimes the numbers are just made up to pretend that no heat or sound would be produced. So just be careful. But if we want to take a realistic standpoint there, definitely some heat and sound would be produced. All right, so define each type of collision, right? This is just reminding us of what each one means. So in an elastic collision, all that means is that kinetic energy was conserved. The total kinetic energy in the system before is the same as the total kinetic energy after. It might have been transferred between the objects. Maybe one gained a little kinetic energy and one lost a little kinetic energy, but the total stays the same. And that's it. That's all there is to it. Whereas in an inelastic collision, kinetic energy is not conserved. The total initial kinetic energy of all objects is not the same as the total final kinetic energy of all objects. Again, the total energy in all of its form is conserved, because conservation of energy is another law of physics, right? But it doesn't all have to stay kinetic, and it also doesn't all have to stay in the system. It can leave as sound and heat and all that stuff. Okay, but don't forget, in both of these, momentum is still conserved, right? That's what makes conservation of momentum so powerful, is that even in an inelastic collision, momentum is still conserved. So in both, total momentum initial will still equal total momentum final. Okay. And then how do you distinguish between them? We kind of just talked about it, right? How do you do it quantitatively? That means with numbers and calculations. It's just check if this is true or if this is true, right? That's it. So you add up the kinetic energy of every object before and see if it's the same as the kinetic energy added up for every object after, right? And we can calculate kinetic energy with just mv squared over 2. So do that for every object before and do it for every object after. Add them up before, add them up after. If you get the same number, then it is elastic. If not, then it's inelastic. And that's really all there is to it, right? If kinetic energy was not conserved, it cannot be an elastic collision. Qualitatively, meaning like with, characteristics, the things you could describe with words about the equation, well, that's just saying, right? There's one type of collision or interaction that even has a shot at being elastic, and that is hit and rebound, right? Where the two objects hit and then don't stick together and bounce off of each other. So if they hit and bounce off of each other, it has a chance at being elastic, but it could totally still be inelastic, right? If these two had bounced off of each other, there probably still would have realistically been heat developed. So in that case, we still do need to must check if the total initial kinetic energy equals the total final kinetic energy, right? It's just that there's a chance that could happen. They could be equal for a hit and rebound. For the other two types, so that's hit and stick, where they hit and they stick together, and then the third one is explosions, where you have one object that splits up into multiple parts. Those are always, they just have to be, based on how they work, they definitely have to be inelastic, right? We talked about it for hit and stick. Explosion's even more obvious, right? If you've got, a bomb or something, it's not moving initially, it has no kinetic energy, and then it blows up into two pieces, right, that move very fast. Since energy is a scalar, those two energies can't cancel each other out, right? It went from having no kinetic energy to having a whole bunch of kinetic energy. Kinetic energy was not conserved. Again, total energy was conserved. It started out as like chemical potential energy in the bomb, then it got converted into kinetic energy and probably heat and light and sound as well. Okay, so quantitatively, just check if total kinetic equals total kinetic final, right? Qualitatively, you know that it can't be elastic if it's a hit and stick or an explosion. It only has a shot at being elastic if it's a hit and bounce or a hit and rebound. All right, let's try a slightly more involved one now, where we've got even the individual momentum we can see here has some X and Y components. But guess what? We're not going to have to learn anything new here. We're going to apply the same principles, the same thing. Total momentum initial in the x-axis equals total momentum final in the x-axis, and then same for the momentum in the y-axis, initial and final. Let's see if we can get started on this one here. All right, so it wants us to determine the final velocity of the smaller, darker ball after the two collide. Okay, so what we've got here is, it's essentially three different pictures. A picture before, a picture while they're colliding, and then afterwards how things look. Okay, so this ball comes in, bounces off, and rebounds that way. Okay, all right. So what have we got going on? We've got this lighter ball. It looks like it's moving perfectly in the x-axis, so that's kind of nice, right? That one's momentum will all be in the x-axis initially. This one, it's all right. It just has components. It has a y component to its momentum and an x component to its momentum, right? We're given the velocities before. We're actually given everything we need to figure out all the momentum initially, right? And then we can figure out the momentum of this ball afterwards, right? And then the only thing missing would be, okay, so what's this thing's contribution? If that's the only thing missing, then we can figure it out. So we know, again, the big idea here is that the total initial momentum will equal the total final momentum in both the x-axis and the y-axis. Let's just start this out with a momentum vector addition diagram to start with, okay? So we've got this lighter ball. Its momentum is perfectly to the right, right? Its momentum is perfectly to the right. And then this one is kind of down and to the right. So maybe I'll draw ball 1 first. Its momentum is kind of down and to the right, like that. So that's ball 1's initial momentum. And then tip to tail, ball 2's initial momentum looks something like that. Okay, so that the net momentum in the system initially, unsurprisingly, is kind of down and to the right. Whoops, that wasn't a very straight line, right? But that makes sense. That's the total initial momentum. Again, checks out, down and to the right, because this is just to the right. This is down, so that's going to introduce some downward y momentum, and also to the right. So overall, our momentum is down and to the right. Okay, now, without even thinking about it, what is our final momentum going to look like? The total final will have to be the same, right? So it's going to look, something like that, because momentum is always conserved. Now we're just getting it in a slightly different way here, because now this ball is kind of going up and to the right, while this one is kind of going down and to the right, right? So kind of doing the VAD backwards here, but if we were to draw in momentum of the ball 1 final, it's going to end up looking something like that. And momentum ball 2 final, something like that. That's momentum of ball 2 final. Now what we want to find is this ball's final velocity, right? And that ball's final velocity is off at some angle theta. So we can see that the ball's final velocity has some x component, right? V1 final x. And it also has some y component, V1 final y. Now that x velocity is going to be giving it some x momentum. So that x velocity is going to play a role in making sure that the total x velocity was conserved from here to here. And similarly for the y velocity, right? That y velocity is going to give it some y momentum. And that ball's y momentum is going to contribute to the making sure that the total y momentum here, when added to this one's y momentum, is the same as the total y momentum we had initially. So like I said, we always start simple, right? So, we're not quite ready to jump into this just yet, but I mean, we could find it as we went too. Here's our starting point. The total momentum initial in the x-axis will equal the total momentum final in the x-axis. And the same will be true for the y-axis, right? I'll maybe just save y. It doesn't matter which one we do first, but I might just do x first here, okay? So let's think about this. We've got 2 objects before, and we've got 2 objects after, right? I'm just going to right now, while it's in my head, I'm going to make sure so that I don't forget. I'm going to call this direction positive because we definitely are going to have to worry about positive and negative here, right? These 2 momenta in the y-axis, one's up, one's down. So we're going to need to make sure we give them opposite signs. Otherwise, our math won't work out correctly. In the x-axis, I'll call that positive and that negative, right? But look at the situation we're dealing with here. We've got 2 balls initially. So the total initial momentum in the x-axis will be P1's initial ball 1's initial x momentum plus ball 2's initial x momentum. And that's going to be equal to, well, once again, afterwards, we still have 2 separate objects. So the total x momentum final is the x components of their final momentum added together. Okay, that's the basic starting point. That's the situation we're dealing with. So if we break those down, right, what is momentum 1 initial in the x-axis? Well, it's mass 1 times object 1's initial x velocity, right? Whoops, I forgot a 1 there. V1 initial x, right? Same thing for momentum 2 initial in the x-axis. It's mass 2 times velocity 2 initial in the x-axis, right? And then momentum 1 final in the x is, well, mass times v1 final x. Momentum 2 final x, mass 2 v2 final x, right? And so see where we're headed here, right? See, look at this. Well, this equation, right? I know we don't have it directly yet. We're going to have to do some trigonometry to figure out what the actual x component of this and this is. But we're basically, like, we've essentially have those. We're just a SOHCAHTOA away, right? So we know the masses. We know every x velocity except for this one, which is the x component of the velocity we're trying to find. So we know everything in this equation except for v1 final x, right? Meaning we can find v1 final x with this setup. And once we've got that, we can repeat in the y-axis, and that's the only thing we won't know in the y-axis for the conservation of momentum in the y-axis calculation. So we can find this x component, we can find this y component, and we'll have 2 sides of this velocity triangle, meaning we can just do the Pythagorean theorem to find the velocity itself. So essentially, we're trying to, I think of it like, we're trying to build this triangle, essentially, right? We'll find the x component by figuring out what it would need to be for momentum to be conserved horizontally. We'll find the y component by figuring out what it would need to be for momentum to be conserved vertically. Then we can Pythagorean to get the magnitude, and SOHCAHTOA use trigonometry to get the direction, the angle, okay? So let's start going to work on this, right? We are going to need, we're going to need those x components. Well, that's just a quick trigonometric calculation. So for each of those velocities, let's go ahead and get their x components. While we're here, we know we're going to need their y components eventually anyway, so we might as well get those now too. So let's look at this one here, okay? Velocity 1 initial. It's headed down like this. Now, they've tried to be a little bit tricky here. They've showed us that this angle is 40 degrees, but that's not the angle that, like, this is headed at, right? But we can use some geometry here to figure it out. One way you could look at it is, you know, if you kind of think about that, that's the horizontal. So draw the vertical, that's 90. And then since all 3 angles in a triangle always add to 180, right? We've got 180 minus 90 is 90 minus 40. This must be a 50-degree angle here. So that must be a 50-degree angle with the vertical. One way to look at it, right? So now we know that angle's 50. Let's just draw in the y component of that velocity. It's downward, right? So that's v1 initial y. And the x component is to the right, like that. And they've told us that the actual velocity itself, right, this velocity at an angle here is 0.90 meters per second, okay? So look at this. We know the hypotenuse of the triangle. We have the angle. We can find these x and y components. We can separate this into its verticalness and its horizontalness, okay? So let's just go ahead and do that. The x component is opposite. This is our hypotenuse. So opposite hypotenuse, that sounds like a job for sine. So the sine of 50 degrees is equal to the x component of that initial velocity over the initial velocity itself, 0.9 meters per second. So multiplying both sides by 0.9 meters per second, we get that the initial velocity in the x-axis is just sine of 50 times 0.9, which gave me 0.68944 meters per second to the right. I mean, we could say at 0 degrees, because remember, 0 degrees is the positive, like it's that x direction. 90 degrees would be straight towards the top of the page, 180 towards the left of the page, 270 like that. So we could just say 0 degrees since they didn't actually tell us anything about like right or east or anything like that. But the important thing here is that's our positive x direction. So when we go to put that into our equation, we'll make it positive. Okay, let's now do the same thing for the y component. Since we're here, we know we're eventually going to need it for when we do the conservation of momentum in the y-axis. So we might as well just find it while we're thinking about this. For the y-axis, it's adjacent, and we're given the hypotenuse. So the cosine of 50 degrees will equal this over 0.9, like that. And therefore, the initial y component is just going to be cos of 50 times 0.9, which gave me 0.5785 meters per second. But I've forgotten something important here so far, because this is downward, right? The y component here is towards the bottom of the page at 270 degrees, if you will, okay? So that means how I've set up my directions, that's my negative y direction. So I need to catch that, right? It won't come out of the math. I need to make sure I put that negative in there, okay? So there we go. We've separated this one into its x and y components, right? Looking at our situation in the x-axis here, again, we've got all of the masses, right? We've now got v1 initial x. v2 initial x is easy because it's just this velocity. It's entirely in the x-axis. If we just got this thing's x component, the only thing we wouldn't know would be one of the things we need to find to start figuring out what object one's final velocity is. So let's now do that same process just to separate this into its x and y components, this velocity here, and then we'll be ready to just jump in with the conservation of momentum. Here we go. So for this one, we're told that the angle's 35, no geometry tricks there, right? Horizontal and the direction of the velocity make a 35-degree angle. So horizontal in the direction of the velocity make a 35-degree angle. So once again, just some trigonometry here. Now x is adjacent, okay, and y is opposite. So we can find x with cosine because we have the hypotenuse and we want the adjacent. We can find this with sine because we want opposite and we have the hypotenuse. So I'll just set those up. Same idea there, nothing new, right? Again, cos is adjacent over hypotenuse, so multiply both sides by hypotenuse and we can get this adjacent side. Okay, just did it for both at the same time. Now if I go ahead and calculate this, 0.7 times the cos of 35, I get 0.57341 meters per second, right? At an angle of 0 degrees straight to the x-axis, okay? So we'll make that positive again because that's what we defined as our positive x direction. And then for the y-axis, I got 0.40150 meters per second. Again, I'm going to throw that negative in there because that's what we're calling the negative y direction, right? We also could have just said like V2Fy is 0.40150 meters per second at 270 degrees, because again, that's straight down. But I'm just thinking ahead to when we're actually doing the math, and I don't want to forget the negative, so I'm just putting it in there, right? If it was our final answer, we would want to give the actual angle direction, but we're just going to use this in our conservation of momentum calculation, so I'm just going to be practical there and put in the negative, because realistically, that's what I need to do for the math steps that are about to follow. That's what I'm concerned with, is making sure I give opposite directions, opposite signs. Okay, so looking at this now, right? There we go. We now know everything except for one of the pieces of the triangle we need to eventually figure out what this velocity itself is, right? So let's just go ahead and put in our, well, first we'll isolate V1 final x, but then we can put in our numbers and we'll have it. Okay, we'll just have to calculate. So here we go. Let's isolate V1 final x. So subtract this from both sides because it's being added to m1 v1 final x, right? And we can pause here for a sec. The physics is speaking to us through the math, right? Look, here, this is the total initial x momentum. And we're taking away the final x momentum that's in object 2. Since we know the total initial had to equal the total final, if we take the total initial and subtract the momentum that ended up in object 2 in the x-axis, we should be left with the momentum that's in object 1 in the x-axis. Aha! Okay, almost there. Now it's being multiplied by mass 1, so we need to divide both sides by mass 1. Giving me that, and now it's just time to put in our numbers. Okay, being very careful about opposite directions, getting opposite signs. In the x-axis, it's a little bit easier because everything was just to the right, which we called positive. So all those velocities are positive. So let's go ahead and plug in the numbers we have. Okay. So mass 1 is 0.15 kilograms, okay? And then we found that mass 1's initial velocity in the x-axis, right? That's why we found these components. We found that it was this, 0.68944 meters per second. So we're going to multiply that by mass 1 there, right? And then we'll just continue on. So do the same for mass 2 times our V2 initial x, okay, but V2 initial x is just V2 initial, right? It's entirely in the x-axis. All x, no y. So we can just do 0.26 kilograms times 0.54 meters per second. And then we've just got to subtract mass 2 times V2 finals x component, which we found here by separating this into its x and y components. So 0.26 kilograms times that x component velocity. So there's our numerator, and now we just got to divide it by mass 1. So divide by 0.15 kilograms. Now, we just need to put this in our calculator. I would recommend breaking it up into steps, right? Don't try to put this all into your calculator in one big step. Multiply these together, hit enter, get your result. Multiply these together, add it to that result, and then multiply these together, subtract that, right? And then divide it all by 0.15. But when I put that into my calculator carefully, I got that V1 final x was 0.631529 meters per second. We got a positive. That's a good result, right? We were predicting that it was... The diagram showed us that it should be in the positive x direction, okay? So that's good. We feel pretty good about that, okay? So looking at where we are now, right? We wanted to build this triangle. Well, we've got this side, right? Now we just need to find this side, and if we did that, we could do Pythagorean theorem to get the actual velocity itself, which is what we want to find. So how are we going to get the y component? Well, same thing, but in the y-axis. We know that total momentum is conserved in the y-axis as well. So we can start there and figure out what this thing's vertical velocity would need to be to make sure that the total y momentum here is the same as the total y momentum here. So let's jump into doing that now, here where I have some room. So total initial momentum in the y-axis will equal total final momentum in the y-axis. Start basic, right? Now we can say, all right, we had two objects initially and two objects finally, so add up their y components before, and you've got the initial total y momentum. Add them up after, you've got the final total y momentum. So that gets us to here, and once again, right, we knew that we had all of this stuff, right? We have all of this stuff, except for the one thing here we're trying to find, which is the y component of object 1's final velocity. Okay, so let's go ahead and solve for that, and then we can plug in our numbers, and we'll have two sides of our triangle. So subtract this from both sides, and then divide both sides by the mass of object 1. Getting us to here, and now we're ready to just put in our numbers. So V1 final y is going to be mass 1, which is 0.15 kilograms, times its y component of its velocity. Now here's where we got to be a little more careful. We need to make sure we make that negative, since we called the y direction downward, we called that negative, okay? So I'm going to do 0.15 kilograms, but again, I'm calling down negative and up positive on the y-axis. So I'm not going to multiply by 0.5785, I need to multiply by negative 0.5785. meters per second. And then, look at this, I just realized, okay, so you might have been screaming at your screen, hey, this is 0. This is 0. You can just cancel it out. We totally could have. We can also realize now that, oh, velocity to initial y is 0. This isn't moving up or down initially, right? Its velocity is only to the right. It's not going up or down at any speed at all, right? So this is actually just 0. So we can just get rid of that. That's 0, right? We're adding 0 there. All right, so then we can just move straight on to this. So minus mass 2 v2 final y, so that's 0.26 kilograms, times its y component of its final velocity, which is also downwards, so negative 0.40150 meters per second. Okay, and notice you will straight up get the wrong answer if you aren't consistent with your signs, right? It's not as simple as, oh, I would just have to add a negative after, right? Because we're actually like subtracting this. And if we subtract a positive or subtracting a negative, we get different numbers. Not just the right number, but the wrong sign. We'll actually get a completely different number. Okay, divided by mass 1, which is 0.15 kilograms. Now, very carefully, we're going to put that in the calculator because we're dealing with some negatives there, and that can often lead to calculator mistakes. So again, I would multiply these, write down the result, or save it in your calculator, right? Then subtract the result, then divide by 0.15. And when I did that, I got that the y component of object 1's final velocity is positive 0.11743 meters per second. So this came out to be a positive. Now, is that a good sign or a bad sign? That's a great sign because we know this had to be moving upwards, right? Based on the diagram, okay, and also based on the fact that this was too big downwards, so we needed to cancel it out a little bit, right? I mean, we didn't actually calculate that momentum, but if we did, we'd see that it was larger than the initial y momentum in the system. So that has to get canceled out a little bit by this to preserve the initial y momentum. Okay, so that positive is a very good sign. We were expecting and hoping to get a positive y component velocity for this guy based on the diagram. All right, so look where we are now, right? We've got this side of the triangle. We've got this side of the triangle. We can now find the velocity itself, what we're actually looking for with the Pythagorean theorem, right? It's close. It's getting exciting. We're almost done. So step 3, if you want to call it that, I just kind of think of it as step 1, we found its x component. Step 2, we found its y component. Step 3, we'll actually find the magnitude of that velocity itself, okay? At this stage, I usually find it's helpful because we've done so much. We've had to work on this so much. I find it's helpful to just really quickly redraw the vector that we're actually looking for, just so we can clarify what we know, what the numbers are. We can see them nicely in one place, right? So we're looking for V1 final. We know that its x component is this, right? We found that with conservation of momentum in the x-axis, and that its y component is this. We found that with conservation of momentum in the y-axis. So again, look, we know two sides of the right angle triangle, okay? We're going to be able to find the vector itself with the Pythagorean theorem. Don't forget, we're looking for a velocity too. Velocity is a vector, so we're also going to need to find the direction. But first, let's get the magnitude using the Pythagorean theorem. So this hypotenuse squared will be equal to these two sides squared and then added, right? And then therefore, V1 final itself is the square root of that. So putting in our numbers, and then squaring them both and adding them. This is what I got after squaring this, adding together. Notice again, we're squaring meters per second, giving us meters squared per second squared, right? But then we're going to take the square root, so that's good. We are going to get units of meters per second out. And, ooh, it's exciting, all this work, and we're about to get our final answer. I got that V1 final was 0.64236 meters per second. Okay. Now, we're almost done, but that's a velocity, which is a vector, so we also need to give a direction, okay? But that's why we've got our nice diagrams. They make it easy to see how we can figure out the direction, right? What is that angle? So finally here, step 4, we're going to get, again, it's nothing official about calling it step 4, but I just thinking of it as the next and last thing we need to do is get that angle. Now, we can see that we've got opposite written out nicely here, adjacent written out nicely here. We also technically have the hypotenuse, but like I said, there was one more calculation involved in getting that, so these just feel a little bit safer. So opposite and adjacent, we can use tan. So tan of theta equals opposite, y component over adjacent, x component, and therefore theta itself will be the inverse tan, second tan of that, which gave me that theta was 10.5 degrees. Okay, so we did it. We've got the magnitude of the final velocity. We've got its angle of direction now. All that's left to do is put them together with sig digs and units and all that kind of wrapping up and putting a bow on it type of stuff. So sig digs, looks like we only get 2 sig digs. Okay, angles, typically the sig dig rules for angles are a little weird because sine, cos, and tan kind of give us some strange things. So honestly, for angles, don't sweat the sig digs too much. I might just go to 2 sig digs for that as well, or to the nearest degree often works as well. Okay, but here we go. So putting those two ideas together, our final velocity is 0.64 meters per second at an angle of, and I could say here, I got to be careful because remember, if I just say 11 degrees, remember this is 0, then counterclockwise to 90, 180, 270. So if I just say 11, they're going to think we mean starting from 0, go 11 degrees. Now, sometimes that is what we mean, and in this case, that actually is exactly what we mean, right? From the positive x-axis is always how those angles are measured. So if we look here from the positive x-axis, yeah, we really are going 11 degrees, right? For example, this one, we couldn't just say 35 though, because then they would think we meant 35 degrees like that, and our angle would be pointed like that, right? So for this one, that wouldn't work. We'd have to do 360 minus 35 to communicate that correctly, right? We'd have to go all the way around, but stop 35 degrees short of a full 360. Anyway, for this one, 11 degrees will work. You could also say things like 11 degrees above the horizontal and stuff like that. But either way, there is our final answer. So like I said, folks, I know it gets long, okay? I know this is a long type of problem, okay? But if you really think about it, it's not super complicated ideas, right? It's really not. It's just that the total x momentum is the same as the total final x momentum, right? And then we do trigonometry to find those x components, right? So that we can add x's to x's. Trigonometry. Oops, sorry, I think the video got cut off there. But I was just saying, right, trigonometry to get the y components so we can do conservation of momentum in the y-axis. Yes, the steps can be like long, and I know there's like a lot of little things to do, but big picture, all we're doing is total initial momentum in the x equals total final in the x. And use that to solve for the pieces of the puzzle we need, right? Same in the y, then put them together with our 2D vector stuff, right? It's just Pythagorean theorem, trigonometry, and conservation of momentum, okay? Sure, there's a few steps, there's things to keep track of, but ultimately, that's what's nice about physics is we're actually applying fairly simple ideas at the end of the day, right? They can take us to some problems that can look a little intimidating, sure, right? But the ideas underlying it are always kind of the same fundamental basic principles. And that's why I always say, right? Do not start here. I'm a physics teacher and I wouldn't start there, right? I start with what I know fundamentally has to be true, which is a very simple idea. Momentum is conserved, right? That's where I would start. Then you can follow that path. Add up all the momentums before, add them all up after, right? Separate the components that you need to, and solve for the unknowns. Which, again, is what our VAD was telling us to do from the very beginning here, really, right? If we take a look, notice momentum 1 initials y component, plus momentum 1 initials x component, right? If we add up the two x components, what do we get? We get the total initial x. And we know that has to be the same as the total final x, which again, we can see is just total 1 final x plus total final 2x, right? Add those two vectors together, you get the total final. Add these two vectors together, you get the total initial x. Same in the y-axis, right? All of the y momentum initially came from object 1 because it was the only one moving downward, right? But if you add up the final y momentum, right, this thing's y component plus this thing's y component, Add those two tip to tail. What do you get? You get momentum. Whoops, I drew that the wrong way. You get momentum finals y component, right? So that's, again, just applying the law of conservation of momentum in each axis separately and solving for what we don't know. All right, should we try out another one? So let's take a look here. So it says a firecracker is shot straight up. At its maximum height, it explodes into 3 parts. A quarter of the mass moves at 62 meters per second horizontally to the right. Half the mass moves vertically upward at 41 meters per second. What is the velocity of the third section immediately after the explosion? Okay, so let's just think about this a bit. A quarter of the mass is going to move afterwards, 62 meters per second, perfectly horizontally, right? So that thing's momentum is all in the x-axis. The other piece, so the second piece, is going to move vertically upward. So that thing's momentum is all perfectly in the y-axis, right? It's straight up. And there's some third piece that we need to figure out what its velocity will be. Okay, now there's another key piece here. It's at its maximum height and it was shot straight up. So do you remember from physics 20, right? Or even just kind of thinking about it, how fast would it be moving if it's at its maximum height and it was shot straight up? So it was moving straight up, but then it reached its maximum height. So it was going up, 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 right? It wasn't going side to side. It has no sideways velocity because it was shot straight up. So there's no sideways force to cause it to start moving sideways, right? So it still will just be, it's going up, 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 getting slower and slower and slower because of gravity, right? Of downward force causing it to accelerate downward. So getting slower and slower and slower. And then at the max height, it's going to stop, right? And then gravity would continue to act on it and bring it down, 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 right? But at the max height, its velocity is 0. Because if it was still moving upwards, well, then it wouldn't be at its max height yet, right? And if it had already started moving downwards, well, then it wouldn't be at its max height anymore, right? It would have moved down from there. So that's great to know. Before the explosion, it wasn't moving at all. That actually makes our life much easier because now we know that before the explosion compared to after the explosion, right? Before the explosion, the initial velocity was 0 and therefore the initial momentum total is 0, right? There's only one object and it wasn't moving before the explosion, okay? Now, sometimes students will say to me, hey, Mr. Maxwell, on this example here, they'll say, wait a sec, how could momentum be conserved here? Because it was moving upwards, and now it's not moving, so didn't its momentum get destroyed? But don't forget, right, this would not be considered an isolated system. There's an external force acting to change its momentum for this part, the part of its journey where it's being shot up into the air and reaching its max height, right? Gravity is an external force acting on it to remove momentum from the firecracker, right? And so momentum is being removed from our system here, the firecracker, by an external force, okay? If we actually were to zoom out and examine a bigger system, in this case it would be the momentum and the earth, sorry, not the momentum, the firecracker and the earth itself. Believe it or not, right, as the firecracker is shot away from the earth's momentum is slightly changed as well from pulling on the firecracker, right? We know that gravity is a mutually attractive force, so the firecracker does have mass and it ever so slightly pulls on the earth upward, okay? So while the earth takes away the firecracker's upward momentum with its gravity, the firecracker actually gives the earth an ever so slight upward pull, okay, equal and opposite pull to how the Earth's pulling on it by Newton's third law, giving it some upward momentum to negate the fact that the Earth took away the firecracker's upward momentum. So momentum was conserved for the system there. Why don't you notice the Earth go flying up then? Well, because its mass is so big that the change in velocity is so tiny, right? So even though there is an almost imperceptible change there, it's so small that you would never notice because the Earth's mass is so big. Anyway, getting
a little bit, I mean, not off topic, but that's not super relevant to how we're going to analyze this question, because now what we can say is, all right, so the firecracker reaches its max height, and then right at that moment, it explodes, right? And on these short time scales, if we look at the instant just before the explosion and the instant just after the explosion, okay, we can say that momentum is conserved. We know that eventually gravity will act on those pieces to change their momentum again, right? Gravity will be an external force changing their momentum. But on these short time scales, in the instant just before the explosion and just after the explosion, we can say this is, approximates an isolated system and therefore apply conservation of momentum. So the great thing here is that the total initial momentum is 0. So without even thinking about it, if the total initial momentum is 0, what's the total final momentum? It is also 0. Whoops, I accidentally said meters per second for my momentum here. That should, of course, be kilogram meters per second. Okay, now how's that going to be the case? Let's think about that a little bit. Well, we know that it's exploded into 3 parts, right? We know that 1/4 of the mass moves at 62 meters per second, horizontally to the right. So let's draw one fragment of this exploded firecracker, and it's going to be moving at 62 meters per second horizontally to the right. So that is perfectly in the x-axis in the instant after the collision. So let's just call that piece 1. Just call it piece 1 because it was the first one mentioned in the question. So V1 final is just 62 meters per second, and it's perfectly to the right. It's entirely in the x-axis. Okay, when it comes time to do the math, I'm just going to do it now before I forget. We'll call right the positive x direction, left the negative x direction, up the positive y, down the negative y. All right, what else do we know? We know that 1/2 of the mass moves vertically upward at 41 meters per second. So half of the mass we started with is going to be moving vertically up. I'll call that V2. Okay. And that's at 41 meters per second straight up. All right. So what does the third piece need to be moving like? I'm going to give you a second to think about that. Remember, initially we had no momentum at all, right? So we've suddenly now got some upward momentum and some rightward momentum. So if I stopped here, could momentum be conserved? No, definitely not, right? Nothing's canceling out this upward momentum. Nothing's canceling out this rightward momentum. So in order for there to be no momentum at all, which we know there is because momentum's always conserved, however the third piece is moving, it needs to be canceling out this thing's upward momentum and this thing's rightward momentum. Now, a very common student mistake here is to say, okay, so this must be moving, this third piece must be moving 41 meters per second down and 62 meters per second left. Do you see the mistake there, though? Is there any law of conservation of velocity? No, there's not, right? No one said velocity had to be conserved. Momentum has to be conserved. So depending on the mass of this and how it compares to the mass of these, right, it won't necessarily be moving with the same velocity, right? It will need to have, though, need to have exactly as much downward momentum as this has upward momentum in order to cancel that out, right? To cancel out this y momentum, this is the only other object that can do it because this doesn't have any y momentum, right? So this one must have downward y momentum equal to this one's upward momentum, and at the same time it must have leftward momentum equal to this one's rightward momentum. Because again, this can't cancel out that rightward momentum and give us the no overall x momentum that we know we have based on how this started. So, putting those ideas together, however this is moving, it must be down and to the left in order to cancel out our y and our x momentum. So this is what we are looking for. We want to know the velocity, the final velocity of that third piece there, right? Since this one's moving kind of uppy and this one's moving kind of righty, and we had no momentum initially, well, this one must be moving downy and lefty to cancel each of those out. Okay, now we weren't actually given the masses, which often means we will be able to cancel them out as we go. Okay, so look at this. We have 1/4 of the mass. This is 1/4 of the mass that we started with. So if we call this m, the total mass we started with, right, then this is just 1/4 of m, right, or m over 4. This is half of the mass, it says. So this is 1/2 of m. And then what does that make our final piece, right? We started with 1 whole mass. We've accounted for half of it, and then another quarter. So a half plus a quarter is we've got 3/4 accounted for, meaning this third piece must have a mass of 1/4 m. Okay, so we've got 2 equal masses and then one that's twice as large as those two. All right, let's draw a vector addition diagram to see what we are dealing with here, okay? And then we can go ahead and jump in with the calculations for the law of conservation of momentum. So if we draw a vector addition diagram for momentum before, there's actually nothing to draw. There's no momentum initially before the explosion, right? It wasn't moving. So that was the easiest VAD we'll ever draw. There it is, nothing to draw. But after, things are a little bit more interesting. Now we know that if there was no momentum initially, there will be no momentum finally, right? That's a law of the universe, okay? Doesn't mean the individual objects might not have momentum, but it does mean that those momenta need to cancel each other out to give us the 0 total that we started with, okay? So if we think about this, we can see that, right? On a VAD, to have 0 total means that we just end up back where we started on our vector addition diagram, so that there's no total to draw, right? So if we think about this, our piece 1 has a momentum to the right, so I'll call that momentum 1 final, and then tip to tail. Piece 2 we know went straight up, so that will be the direction of momentum of piece 2, and then hey, just like we said, momentum 3 needs to cancel out both of these, right? So momentum 3, sure enough, downy lefty takes us back to where we started. That's the momentum of piece 3 final, okay? And sure enough, right, we're back to where we started. If we went to draw in the net momentum now, net is always drawn from where we started to where we finished. Well, we started exactly where we finished, so there is no net momentum to draw. And so one thing to notice here, look, right, this is exactly what we said. If we were to split momentum 3 final into its x component, well, its x component would look like that. Notice it's the exact size as momentum 1 final, but in the opposite direction. Well, that's what we said had to happen, right? Since momentum 1 is the only thing with an x component, momentum 3 is the only other thing with an x component, they have to be canceling each other out. This can't cancel out any x momentum to preserve momentum in the x-axis. It's moving straight up, right? And then conversely in the y-axis, look, if we find the y component of momentum 3 final, it would just look like that. And look at that, it's the same size as momentum 2 final, but downwards. Again, all the same logic, but vertically, right? This can't cancel out y momentum, it's moving straight to the right. So since this does have some upward y momentum, this needs to have the exact same amount of downward y momentum to cancel each other out and preserve momentum in the y-axis. Now another thing you could notice here, okay, if you look in the filled in notes, the filled in notes that contains extra examples, you will see me actually solve it this way as well. I actually solve it both ways in those notes just to show you both ways. But one thing you could notice here is that this is actually a right angle triangle, right? This makes a 90-degree angle because this is straight up and this is straight right. So this is a 90-degree triangle, meaning we could actually just use the Pythagorean theorem here, see if and get the masses to eventually cancel out. You'll see that it works out to find the hypotenuse. And the hypotenuse represents the momentum of the third piece, which would get us pretty close to finding that velocity, right? We just need to get the mass to cancel out, which you'll see in the math it actually does work, right? So we could say that momentum 3 final squared equals momentum 2 final squared plus momentum 1 final squared. And that's just because we drew our vector addition diagram and we noticed this is a right angle triangle. So that's actually a totally valid way to solve it. Okay, for the sake of just kind of, showing you and getting at that conservation of momentum principle and showing you that it really is the same thing, I'll just jump in with the law of conservation of momentum. But if you're curious or if you want to try that out on your own, you can check in the filled in notes and you'll see that it does totally work out that way as well. So there's often not one correct approach with these. As long as you're applying fundamental and sound physics reasoning, right, you can do what jumps out at you. So that is totally a valid approach to this, because we know those vectors do have to cancel each other out. We know these are perpendicular, making a right angle triangle. So you could actually totally just use the Pythagorean theorem from here. Okay. Like I said, though, I think I'll probably just jump in with conservation of momentum. The nice thing here is we don't actually have to separate either of these into their x and y components, because again, this is all x, no y. This is all y, no x. So V2 finals y component is just this, 41 meters per second up. Its x component is just 0, right? And vice versa here. 62 meters per second is V1 finals x component, and 0 is its y component, okay? This has both x and y components, and that's what we're going to do to solve this problem, right? We can apply conservation of momentum in the x-axis, and that will let us find V3 finals x component. Sorry, I know that writing is tiny. I'm just trying to squeeze it in there, right? And then we can apply conservation of momentum in the y-axis, and that should tell us V3 finals y component. And notice, right, we're doing the same thing with the x component, which we'll get from conservation of momentum in the x-axis, and the y component, which we can get from conservation of momentum in the y-axis. We'll have two sides of this triangle. Then we can use Pythagorean theorem to get the hypotenuse. And finally, trigonometry to get the actual direction, because they asked for velocity, not speed. So we do need to give direction because velocity is a vector. All right, so there's the plan. I'm going to do x-axis first. No reason that we have to, but I don't know. I'm just going to do x first. You could totally do y first and it would be the same result. We got to find them both eventually, right? Our goal is now to essentially build that triangle one piece at a time. So let's go ahead and find the x component using the conservation of momentum in the x-axis. So as always, right, again, we're not going to jump to some big fancy equation right off the bat. That's how we get, overwhelmed and stuck. Apply the simple idea, the simple physics principle that we know has to be true. In this case, well, we know that the total initial momentum in the x-axis will have to equal the total final momentum in the x-axis, right? Now, here's the nice thing about this one. What is the total initial momentum in the x-axis? Yeah, it's 0. It wasn't moving at all. It definitely wasn't moving side to side. So this whole side of the equation is actually just 0. So 0 equals, and then what's the total final momentum in the x-axis? We've got 3 objects, right? So the total final momentum will just be the x component of each of their final momenta, okay? And you might be screaming at your screen right now, hey, one of those is 0. And you're right. One of these is 0. One of these has no final x momentum. Which one? Object 2, right? This is moving straight up. This doesn't have any horizontal momentum. So our equation just got even simpler. That's 0 as well. So here's our situation, right? And so let's now find the momentum. Since we're looking for velocity 3 final, right? Let's isolate momentum 3 final. So I'll subtract momentum 1 finals x component from both sides. And we get this equation here, right? Which once again, look at the physics speaking to us through the math now, right? This is exactly what we predicted. Momentum 3, momentum of object 3 in the x-axis had to be equal but opposite to momentum 1's final x component, right? The momentum of this thing's in the x-axis, so that they could cancel each other out and give us no overall x momentum, because that's what we started with. So always good when we see what, the physics ideas we applied kind of come back to us in the math, right? Tells us we're thinking along the right lines. These momentum do have to be equal and opposite to cancel each other out and give us no momentum in the x-axis, because we started with no momentum in the x-axis. Okay, so every p is just an mv, so what's momentum 3 final x? It's mass 3 times velocity 3 finals x component. And then same thing here, All right, and we're solving for the x component of velocity 3 final so that we can eventually find velocity 3 itself. So divide both sides by mass 3 and we get that. So now we've just got to plug in those numbers. So V3 finals x component will be, okay, there's a negative that's part of our equation here. So negative mass 1. Now again, we don't know what mass 1 is, but we know that it is 1/4 of the total mass, right? So mass 1 is just 1/4 m. V1 final x, well, that's just V1 final. It's all in the x-axis, so times, and again, we were calling right the positive x direction. That is to the right, so I'll call it positive 62 meters per second when I put it in the equation here. So positive 62 meters per second divided by mass 3. Now again, we don't know what mass 3 is, but we know that it's 1/4 of the total mass. So mass 3, yes, but that's just 1/4 of the total mass. And look at that, right? When we have these masses that are in terms of each other or in terms of some total, they often end up canceling each other out, right? Because when we're looking for a momentum, we know that we'll have, if we're looking for a velocity and we're using momentum, we know we'll eventually divide both sides by the masses of the object, right? To get the velocity by itself. So in that case, if all the masses can be expressed in terms of the same variable, like they could here, they could all be expressed in terms of the total mass, well, that means we're going to be dividing that variable on both sides where it already exists, so it will cancel out, and sure enough, it does here. So we don't need to know what the actual mass was, we just need to know how big they are relative to each other. So 1/4 of the mass divided by 1/4 of the mass, well, that's just 1. Those cancel each other out. So velocity 3 finals x component is actually just negative 62 meters per second, right? Or 62 meters per second. The negative for us, that's the negative x direction, which we said was going to be left, right? Now that makes a ton of sense. If we think about it, right, here it did end up with the same horizontal velocity as this one. Again, that's not its overall velocity because it also has this vertical component, but its horizontal velocity did end up being the same as this thing's because they have the same mass. So to have the same horizontal momentum, they're going to need the same horizontal velocity because the masses are the same. So momentum is just mass times velocity. So if it's got the same mass, it needs the same velocity but in the opposite direction to get the same momentum but in the opposite direction in the x-axis. Now, when we do this in the y-axis, that's probably not going to be the case because, in fact, it won't be because they don't have the same masses. In fact, we could even make a prediction here. This has, 1/4 is half of a half, right? So it has half as much mass as this one, and it needs to cancel out with the same amount of momentum. So we could make a prediction. How could it make up for that? Well, if it has half the mass, it must have double the velocity in order to end up with the same amount of momentum downwards as upwards. So that's my prediction. Let's see if it comes true. Okay, but either way, again, we're trying to find this final velocity, right? What it is, this velocity at an angle. To do that, we were kind of building this triangle by finding its components. We've now found its x component. Let's see if we can find its y component using conservation of momentum in the y-axis. So, same starting point, right? Simple. For momentum to be conserved, we know that the total initial momentum in the y-axis must equal the total final momentum in the y-axis, okay? And once again, it wasn't moving initially. So it wasn't moving up or down. It doesn't have any y momentum initially. So that's 0. So the whole left side of our equation now is just 0. And that equals the total final y momentum. Well, we've got 3 objects, so add up the y components of all their momenta, and you get the total final y momentum. And again, we know that has to equal 0 because that's what we started with. And again, one of these is 0. Which one of these does not have a y component to its final momentum? Object 1, right? The one that was moving straight to the right. It only has x momentum. It has no y momentum, so that's 0. So once again, our equation gets even simpler. And then once again, we'll see the physics speak to us through the math here, right? If I subtract the final y component of object 2's momentum from both sides, I end up with this, right? And look what we're saying. The momentum of object 3, its final y component, needs to be the same size, but in the opposite direction as object 2's final momentum in the y-axis. In other words, however much momentum this has up, this needs to have down so that they cancel each other out and there's no momentum in the y-axis afterwards, which we know has to be true because there was no momentum in the y-axis before the explosion. All right, every P is an MV, so let's break these P's down into MVs, mass times velocities. There we go, and then divide both sides by mass 3 because we want to find this y component of this unknown velocity, and we get that. The y component of velocity 3 final is just going to be equal to this, okay? So let's go ahead here and put in our numbers, keeping in mind that we are going to call up the positive y direction and down the negative y direction, okay? So plugging in here, we get negative mass 2. So mass 2 was 1/2 of the total mass, times its final y velocity, but that's just all of it because it was straight up, right? So this is entirely in the y-axis, so positive 41 meters per second because upwards. Whoops, I forgot the negative that was part of this equation. There we go. And then divide it by mass 3, which we know is 1/4 of the total mass we started with. And once again, those masses just cancel out. Now, 1/2 doesn't quite cancel out with 1/4, so be careful. We've got 41 meters per second times 1/2 divided by 1/4. Okay, well, dividing by 1/4, remember, dividing by a fraction is the same as multiplying by its reciprocal, right? You know, x over 2 is the same as x times 1 over 2. Right? So same idea here, dividing by 1 over 4 is the same as multiplying by 4 over 1, or 4. So we could just rewrite this as negative 1/2 times 41 meters per second divided by 1/4, which is the same as times 4 over 1, right? Or if you like, you could put it in decimals. You could say 0.5 and then divide by 0.25. You'll get the same result, but fractions are our friend. They can help us out. Sorry, I'm working sideways here just because I kind of ran out of room. So if we do negative 1/2 times 41 times 4, we get negative 81 meters per second. Sorry, not 81, 82 meters per second. Now, hey, remember our prediction? We said that because this has twice the mass, right, and it's moving up as this one's going to need to have twice the velocity to make up for that so that it still has the same momentum, right? P equals mv. So if this one has 2 times more mass than this one, but they need to end up with the same momentum, this is going to need to have a velocity that's 2 times larger and downward to cancel out this thing's momentum. Sure enough, right? Look what we ended up doing. 1/2 times 4 is 2. We doubled this velocity, right? 82 is double 41. So twice as fast downward as that was moving upward so that they have the same momentum but in opposite directions, canceling out the vertical momentum altogether and therefore giving us the no momentum that we know we started with and we know must be conserved. So it has a velocity of 82 meters per second downward. Okay. So, big picture here, right? Don't lose sight of the goal. We're just chipping away at the same goal here. We were trying to build this triangle. We found its x component, right? We know that velocity's x component. Now we know its y component. Hey, we know 2 sides of a right angle triangle. We can find the third with Pythagorean theorem and finally the direction with trigonometry. So we're almost there, okay? We've got the components of velocity 3 final. Now we just need to actually find velocity 3 final. So like I said, at this stage, I like to usually just quickly redraw the vector addition, the component diagram for the vector we're trying to find, okay? In this case, velocity 3 final, just because often, we were doing a lot over here. We were thinking about other stuff and it can get kind of crowded. So let's now just focus in on that vector that we want to find, right? So we want to find V3 final. What have we found so far? Well, we found its x component, right? We know that's 62 meters per second to the left. So if something's going, downy lefty like this, we know that it's now going how fast it's going left is 62 meters per second, and how fast it's going down is 82 meters per second, right? So its y component, this part, is 82 meters per second. Okay, that's not a very straight x component. Sorry, I'll just fix that. There we go, that's a bit better, okay? And by definition, the x and y axis make right angles with each other, so we have a 90-degree triangle. So we can use Pythagorean theorem to get the magnitude of V3 final, right? So V3 final squared is going to equal 62 meters per second squared plus 82 meters per second squared. So square root both sides and then square those and add them, and we will have the magnitude of our final velocity for the third object. So squaring these two and adding them, I got 10,568 meters squared per second squared because we squared those meters per second. And then to square root them, because remember, we don't want V3 final squared, we want V3 final. So square rooting both sides, that gave me that V3 final, how fast object 3 was moving, is 102.8008 meters per second, right? So if it's moving 102.8008 meters per second at this angle, that means that horizontally it's moving 62 meters per second to the left, and vertically it's moving 41 meters per second down in the instant right after the explosion. Now we're almost done, but is this a complete answer for a velocity, which is a vector? No, right? It needs a direction. Is it good enough to just say downy lefty? Well, no, because again, downy lefty is a lot of directions, right? That's downy lefty, that's downy lefty, that's downy lefty. We need to be more specific. We need an angle. So that's our final step to get the direction, which will be an angle here in 2 dimensions. And again, this is why I recommend redrawing the diagram, right? It doesn't have to be something you draw once and be done with. You can come back to it and say, okay, well, how do I describe the direction this is pointing? Because we've drawn this triangle, we can say, okay, well, if I could find that angle, I'd be off to a good start, right? So that angle, our triangle's set up nicely. This is showing us how we can what direction we would need to aim V3 final. We've got opposite, we've got adjacent. Technically, we now have hypotenuse, but again, that was one more calculation, so I like to use these components. Okay, so here we go. Tan of theta will equal opposite over adjacent. And so opposite is 82 meters per second, adjacent is 62 meters per second. So taking the arctan or the inverse tan of both sides, right? Inverse tan of 82 over 62, I got that theta was 53 degrees to the nearest degree. Now, got to be super careful here. If we just say 53 degrees, will people think we mean that this velocity is pointed in this direction? Not quite, right? Remember, the angles, how we're pointing the vector, we always start, this is 0, and then we go counterclockwise. This would be 90, this would be 180, right? So a vector pointing straight up is pointed at 90 degrees, pointed straight to the left is at 180, straight down it would be 270, right? So it's almost like if, from math class we talk about reference angles. This is sort of like a reference angle. So we just have to be careful there, because really, right, this is not 53. This direction that we're trying to describe here is not at an angle of 53 degrees. 53 degrees would just mean we were pointed somewhere over here, right? It would mean this was 53 degrees, okay? And that's definitely not what we want. That's actually the opposite of what we're trying to say. This would be up and to the right. We want down and to the left. So we just got to think about, okay, what direction is that then? Well, we are past, we're down and to the right, right? And we can see the angle between our vector and the x-axis. That is what we just found to be 53 degrees. So this is 53 degrees. So what is the angle itself, right? What's the actual angle? Well, we went past 180, starting from 0, right? Starting from the positive x-axis. We went past 180. How far? By 53 degrees. So the actual angle will be 180 plus another 53 degrees, giving us, 233 degrees. If we just say that, people will know what we mean, right? They'll know we mean, okay, so that's kind of down and to the right in the third quadrant, we would say in math, right? So that is now a complete answer. So putting those together, what is our final velocity? V3 final, is, how many sig digs do we get here? We get 2 sig digs. Okay, so I'm going to need scientific notation. So we're going to write this as 1.0, because it's a 2 is follows, so we'll round it down to a 0. 1.0 times 10 to the power of 2, right? So 1 times 100, about 100, to 2 significant digits, meters per second, at an angle of 233 degrees. Okay, and there we go. That is a complete answer for the final velocity. So again, I know these can take some time, right? Because you've got to do the calculations in each axis. Honestly, though, with practice, it starts to become pretty quick, right? You get used to the idea of, okay, total initial x equals total final x. Let me just solve for the unknown in the x-axis, right? Total initial y equals total final y. Let me solve for the unknown in the y-axis. Put them together with the Pythagorean theorem, and then use SOHCAHTOA to find the angle for direction, okay? And again, I know that actual overall solution might look a bit intimidating, but the ideas we're applying here are simple, right? It's just total initial momentum equals total final momentum. Add up all the momentum before in the x-axis, add up all the momentum after in the x-axis, those have to be equal. And since every momentum is just a mass times a velocity, we can figure out unknown velocities using that fact. Okay, so go ahead and try this one. This is one where, again, my advice right away, right, of course, draw your diagram, draw your vector addition diagram, because that can help guide you as you go. But when it comes time to do the math, right, don't overthink it. Don't try to be a hero and jump to some big equation, right? Start simple. Start with this, right? That's the type of thing I want to see anyway in your solutions on a test or on a quiz or anything like that, because you're showing that you understand the basic physics principles and how they lead to it, right? It's not just numbers on a page. You're showing the physics that lies underneath all of these calculations, right? So start with statements like this when solving this. So there's my advice for this one. Okay, and again, my solutions for all of the formatives are always posted, so if you get stuck here, feel free to go look at my solution if you need a push in the right direction, or of course, send me an email, book a meeting, any of that stuff. And feel free to take a break here as well, take a break from my voice and pause and do a couple examples and start to get the hang of it a little bit. Okay, and then we'll finish up here, okay, just kind of wrapping up a bit and talking, reminding ourselves of the big ideas that we've seen and studied here and how we approach them.
All right, so just kind of a reminder here, folks, right? I know like these get long, they can take some time. Keep in mind this on the diploma, this would be worth 1 mark, right? Every question on the diploma is worth 1 mark. They took written response off the Physics 30 diploma, so it's all multiple choice and numeric. Now, that's not to say obviously don't do it, don't try it, right? But if you're getting like stuck on one, if it's bogging you down, if you're taking a long time and you don't feel like you're getting anywhere with one like this, right? Keep in mind, when you're writing a test, right, something like the diploma, it's often a good idea to move on when you're stuck, right? You don't want to burn yourself out on one question, trying it over and over. If you're not sure how to do it, right, move on. You can always come back and look at it again, but you don't want to tire yourself out on one question so that you're not going into the next question at 100%, right? With your brain power all ready to go, okay? So just taking a step back here, reminding ourselves each question worth the same number of marks, right? Same goes for your unit tests, obviously, too. So, which of the following statements best describes an isolated system? Got 4 options here. A, kinetic energy is always conserved in an isolated system. Well, that's actually not even really true, right? Total energy is always conserved in an isolated system, but kinetic energy doesn't have to be conserved in an isolated system. It could be converted from one form to another, right? So that one, I don't think that's a very good definition. Okay. B, momentum is always conserved in an isolated system. Now that's pretty good. That's true, right? That is true. Momentum is always conserved in an isolated system. But always read every option, right? Especially for these ones where you could, especially where it says best. That usually means that like a couple of things will be true here, but they might not be the best way to say it, okay? Option C, only gravitational forces act on an isolated system. Well, that's not true, right? You can have forces acting on an isolated system, right? And they could be gravitational. There's just no net force acting on an isolated system. In fact, if only gravitational forces were acting on an isolated system, it wouldn't really be isolated, would it? Because there'd be no force canceling it out. There'd be a net force, right? It would be accelerating due to gravity. So it wouldn't be an isolated system. Its motion would be changing, the momentum would be changing, the energy would be changing, right? I don't think that's very good for an isolated system. Now look at D. No external forces act on an isolated system. Now that is a pretty good definition, right? That is actually not just a description of an isolated system, it's kind of the definition of an isolated system, right? No net external forces can act on an isolated system. So B is true, okay? And it asks us, why is D a better answer than B? Well, if we're trying to describe an isolated system, right, this is kind of like, this is true, but it's a feature of an isolated system, right? Whereas this is literally the definition of the isolated system, right? If you were to say, I have brown hair, that's true, right? But is it the best definition or description of who I am, right? A better one, would be to actually talk about who I am, what I do, my job, stuff like that, right? Versus just saying I have brown hair. Not that it's not true, but D is the literal definition, whereas B is just a feature of an isolated system. Right? So giving a feature versus the actual definition, that's why D is the best answer here. Not that B is wrong, but it's not the best answer out of the options given. Okay, let's try this one out. So a teacher asked students to make some statements about the differences between elastic and inelastic collisions and how they can be analyzed. Mark the following statements from students as correct or incorrect and provide helpful feedback to the students where necessary. So what did student 1 say? Student 1 said, an inelastic collision is one where energy is not conserved, and thus the problem cannot be solved. Okay, what do we think of this, right? I don't really agree with almost anything that this student has said, right? You can tell they're thinking along that, like they know that in an inelastic collision, they remember it had something to do with a form of energy not being conserved, but it wasn't all energy, right? All and total energy is always conserved. It just might change forms into forms we don't have an equation for, or it might leave the system, right? Maybe as heat or something like that. But total energy is always conserved. That is a fundamental law of physics, right? So what are they thinking of? Kinetic energy. In an inelastic collision, kinetic energy is not conserved. So let's say incorrect, and then we'll give them the feedback, right? So the total energy is always conserved. It's just that. In an elastic collision, kinetic energy is not conserved, right? It's not destroyed, it just gets converted to another form and or it leaves the system. And what about the second half of their sentence here? Thus, the problem cannot be solved. Can we not solve inelastic collisions? No, we can definitely solve inelastic collisions, right? We've done it a few times in this lesson and the previous lesson, right? So definitely it can be solved. It's just that we can't use the law of conservation of energy. We can't use physics principle number 5. Not because it's not true, again, right? But just because it might have converted into a form we don't have an equation for or left the system, and so we don't know, there's unknown values, how much energy left the system. We have no way of knowing, especially if it's in a form like heat that's really hard to keep track of. So it definitely can be solved. We're just going to have to use conservation of momentum, physics principle number 4 instead, right? We can't use conservation of energy. All right, there we go, okay? So we'll give them that feedback. Let's move on to student 2 here. In an elastic collision, kinetic energy is conserved. So far, so good. That's true. That's the definition of an elastic collision. So it will be less work to solve the question with physics principle number 5 rather than the significantly longer principle number 4. That's true, right? If kinetic energy was conserved, we can just say total initial kinetic equals total final kinetic, right? And we wouldn't have to do all this X and Y component stuff, adding the vectors, Pythagorean, right? since energy doesn't have a direction, it doesn't have x or y components, and we can just do one calculation where we say total initial kinetic equals total final kinetic, add them all up, and get whatever we'd want to know, right? Now, there is one important caveat here. So I do agree with this student. They're correct, but they need to be careful too, right? Because what will energy never give us? Since it's a scalar, it will never give us direction, right? So if we were asked to find the velocity, this would not be true, right? We would still have to do principle number 4, conservation of momentum, because velocity is a vector. So we would need to use conservation of momentum, a vector that can give us direction, right? So they are correct, but this stops being true if we need direction for our answer, right? All right, moving on to student 3 here now then. So it makes no difference if the collision is elastic or inelastic if we use conservation of momentum. Well, yeah, that's true, right? The conservation of momentum always works. So correct, yeah, totally, okay? But again, just to comment here, right? If we can get away with conservation of energy, it is a bit quicker because, again, we don't have to do all that x, y axis stuff, right? But it's true. If you use conservation of momentum, you can always use conservation of momentum, elastic, inelastic, explosion, whatever. So if we can use conservation of energy, if we know the collision is elastic and we know that we don't need direction for our final answer, it can be less work to use physics principle number 5, conservation of energy, right? But physics principle number 4, conservation of momentum, will always work. All right, so the last little bit here, honestly, I would recommend personally, I would just pause the video here and try to just fill out these tables yourself, right? It's just getting used to the idea of setting up, looking at the momentum before and after, right? There's obviously no numbers, no actual calculations involved here, but just getting a feeling for like, okay, what types of momentum do we have before in the x and the y axis and after in the x and the y axes, right? I will run through them, but I think it's probably more beneficial to just try it out on your own and then compare with the filled in notes to see if you got what I got, okay? But that's actually it for this lesson. So we'll run through these. Like I said, I encourage you to try it out on your own, honestly. Take a break from my voice. But I will go through them here just in case there's some that you're stuck and you want to hear me explain, okay? All right, so before the collision, we've got these two masses. After the collision, looks like they stick together and move as one object, okay? And it just wants us to say, okay, so before the collision, what would be the expression that would give us mass 1's horizontal momentum, right? The x component of its momentum. Well, P is just mass times velocity. Momentum is mass times velocity, right? So momentum in the x-axis is the mass times the x component of its velocity. So we're given this angle A here. So if we took a look, right, if we were to split this up into its components, its x component would look like that, right? The horizontalness of its velocity vector, and the y component would look like that, the downness, the verticalness of its velocity vector, right? So we could call this v1 initial x, the rightness of its velocity, and this would be v1 initial y. Right? And we've got that angle there, A. So what are the x and y components? Well, let's just take some trigonometry, some SOHCAHTOA, right? The x component is adjacent. We've got, I mean, we don't have the number, but we would typically have this velocity. That's what it's labeled as. So we're writing the momentum in terms of the given variables, right? So the x velocity, we would say the cosine of that angle A is equal to adjacent v1 initial x over hypotenuse, which is just the actual velocity, v1 initial, right? And therefore, v1 initial x is just going to be the cosine of whatever angle A is times v1 initial. That's how we get its x component. We'd multiply by the cosine of that angle. So what's its momentum? This is its velocity in the x-axis. So its momentum in the x-axis will be its mass times that, right? So momentum 1 initial in the x-axis will be mass 1 times the cosine of the angle A times v1 initial. And there we go, right? That's just mass times velocity in the x-axis. I might just rewrite it like this. v1 initial times the cosine of A. There we go. And then we could just set up the same thing to get the y component so that we can get its initial y momentum, right? Find the y component of its velocity, multiply it by its mass, and now you have the y component of its initial momentum. So same thing, except y is opposite to our angle A. So opposite over hypotenuse, we would use sine, right? So sine of A is the y component over the velocity itself, and therefore the y component, multiply both sides by the initial velocity, we get the y component is the initial velocity times the sine of that angle A. So what's its initial y momentum? Well, it's mass times its initial velocity times the sine of A, right? And of course, we'd want to do things like keeping track of direction. So if I said, let's just say down is our negative y, up is our positive y, right is our positive x, left is our negative x, right? Then we would need to make sure we remembered this would actually be negative, right? So we could slap a negative in there once we calculated it out, okay? Let's do the same thing now for mass 2. So there are mass 2's x and y components of its initial velocity. Let's use SOHCAHTOA to, get expressions for those x and y components. Here we go. So hopefully you can see where I got these expressions from, right? Adjacent over hypotenuse would be cosine. So to get the x component, right, we end up with hypotenuse times the cosine, right? Gives us this expression for the x component. For the y component, this, right? The hypotenuse times the sine will give us the y component because the y is opposite. So multiply this by the mass and we have the x component of ball 2's momentum. Multiply this by the mass and we have the y component of its momentum. So let's add those into our table, right? And there we go. So again, those are both going to be positive for how we define directions. So now the total, what's the total x momentum? We would add those two up, right? I might not have room to actually write it out, but that would be the total x momentum, the result of adding this to this. So add those. Same for the y-axis, right? Just being careful about, because in that axis, they actually are in opposite directions. So we would need to remember that this one is negative, right? Okay, which actually makes sense because look, afterwards it's just moving to the right. It only has x momentum. So this thing's y momentum must have canceled with this thing's y momentum, giving us 0 overall momentum in the y-axis, which is then still true here, right? It always will be conserved in both axes. All right, now after the collision, okay, what's the momentum of this one object that is really just our two objects now stuck together? Well, in the x-axis, it's all in the x-axis, right? Like we were just talking about. So sorry, my pen's being a little glitchy. Okay, right? It's all in the x-axis. So all of its momentum is x momentum afterwards. I mean, that was true before, but this had some y momentum and this had some y momentum that were canceling each other out. Now we've just got one object with 0 y momentum, all x momentum. So how do we figure out its final x momentum? It would be mass 1 plus mass 2, that's now the mass of our object, times this new velocity that it has, because that's all in the x-axis, right? We're still multiplying the mass by the x component of its velocity to get the x component of its momentum. It's just that the final velocity is the x component. The x component is the final velocity. It's all x component, no y component. And therefore, what is its final y momentum? It is 0, right? It doesn't have any y momentum final. So what's the total? It's add them all up, but there's only one thing to add here, right? Its x momentum would just be this, m1 plus m2 times v12 final, and its y momentum would just be 0, okay? And the key idea here, the physics principle number 4, is that this and this will be equal, right? Meaning that, like, the x momentum initial will be the same as this, right? These added will equal this. And these added will equal 0, right? It's conserved in both axes separately. All right, so let's move on to this one. Same idea, right? This is just an exercise in getting used to like finding the x and y components initially, how to look for what's the x-ness of the momentum initially total, what's the y-ness, right? And then what is that for the final as well, okay? So here we've got a ball that's not moving. V1 initial is 0. Well, that makes our lives easy, because then what is mass 1's initial momentum in the x-axis? 0, right? If the velocity is 0, its x component is 0, its y component is 0, and therefore mass times velocity, momentum, is 0 in both axes. Mass 2, slightly different, but mass 2 is moving, but it's also just moving in the x-axis, right? There's no angle, no x, y components, right? I mean, there are, but the x component is the entire momentum, right? And the y component is just 0. So since it's not moving vertically, the y momentum initially for mass 2 is 0, and the x component is just going to be its mass times its velocity, because that velocity is vx, right? It's all in the x-axis. So it's just going to be mass 2 times velocity 2 initial. So what's the total, right? Add them up. 0 plus mass 2 v2 initial is just mass 2 v2 initial. We'll call that positive. We'll call the right the positive x direction, left the negative x, y positive negative, like that. And the initial y momentum in this system is once again total 0, right? 0 plus 0. Okay, so right away, right, we know the final is going to be 0 for the y, and it will be the same it'll be the same number as whatever this gives us, right? We're going to have a different expression, but we know that whatever that expression is, it's equivalent to this, okay, mathematically or numerically. So let's go ahead on this side now. We're going to have to do some splitting into x and y axes, but we know how to do that. Let's just jump in with ball 1 there. Right, so there we go, right? Just using our same old idea, SOHCAHTOA there, right? Cosine is adjacent over hypotenuse, so the cos of b will be the x component over the velocity itself. Multiplying both sides by the velocity itself, we get that the x component is the velocity times the cosine of b, right? Same logic for the y component, except it's opposite and hypotenuse that we have, so we would use sine, right? So after the collision for mass 1, what's its final x momentum? Well, it'll be its mass times its final x velocity, right? And same goes for the y momentum, but mass times the final y velocity. So putting those in here, we get that, right? Now for mass 2, same exact idea, okay? We're going to go ahead and split it into its x and y components and then find them using trigonometry. So mass 2's final velocity we can see is down and to the right. So its y component is the down part of that, and its x component is the right part of that, right? Downy righty gives us a righty x component and a downy y component. We'll just have to be careful. Remember, we call down the negative y direction, so we'll need to keep track of that negative when we go to put it into our calculation. So what is mass 2's final x momentum? Well, it's mass 2 times the x component of its final velocity, which we can see is its final velocity times the cosine of that angle A, right? And for the y component, we'll have to put in a negative. Can't forget that that's negative, but then it's just the same idea. Mass 2 times velocity 2 final times the sine of A, because the y component is opposite to that angle A, right? And there we go. So these two added together have to equal 0. Right? Because initially there was 0 momentum in the system. And then these two added together have to equal this, the initial x momentum, right? Which just came from mass 2. So the total in the x-axis final will be the result of adding those. And once again, right, the final x component will equal the initial x component, and the final y component will equal the initial y component. And that's how we can solve for these unknowns, by setting up an equation based in that, right? Total initial momentum x equals total final momentum x, total initial momentum y equals total final momentum y. All right, let's try another one here again, just getting practice with this idea of seeing the components and what trigonometry and summing is involved in finding them and setting up your calculation. So now that we've done a couple, right, if you didn't pause the video and try it on your own, I'd really recommend, now that we've done a couple, right, and you're kind of starting to get the hang of it, pause now, right? Try this one on your own. See if you can separate into the x and y components, right? Think about what the momenta would be before and after in expressions in terms of these variables, okay? So I'll jump into this one. Let's go a bit quicker through here, okay? I'm going to split M1 and M2 into its x and y components, and then we'll put those momenta into the table. Here we go. Right? So just like always, finding the rightness and the downness of this initial velocity, right? V1 initial, we can just use SOHCAHTOA. Hopefully you can see how I got those, right? Just set up a cos equals adjacent over hypotenuse and then multiplied by the hypotenuse, right? But there we go. Same thing here, right? We'll just have to be careful. Notice the y component initial is downward for this one and upward for this one. So when we went to do the math, we would put in a negative for this y component of the velocity, right? So, right, same old, same old. What's the momentum of object 1 initially in the x-axis? It's its mass times the x component of its initial velocity, right? So mass 1 times v1 initial times the cosine of that angle A, right? Repeat for the y-axis, but remember that it's a negative here. So negative mass 1 times v1 initial times the sine of A, right? Just using the x and y components of the initial velocity that we found to find the x and y components of its initial momentum, which is just those components times the mass, P equals mv. For object 2, we get this, right? Those components times the mass of object 2. So what's the total initial x momentum in the system? It's the result of adding those, right? Add those two numbers up. Two objects, they each have an x momentum. So the total momentum in our system is just the sum of each of those two objects' x momenta, right? Same for the y, except obviously the y components. Okay, and so whatever those add to, whatever the x component adds to, we know it's the x momentum of this one object's, well, x momentum, right? These two initial x momenta have to add to give us whatever the x momentum of this object is afterwards, because momentum is always conserved. So the expression might be different, but we know that the numbers come out to be the same. Let's figure out the expression for this thing's x and y momenta. Here we go. But same process, just using trigonometry, right? And there we go. Cos is adjacent over hypotenuse. So this adjacent would be the cos of c times that hypotenuse. Okay, and just again being careful, the y component here is downward. We called that negative. So when we go to do the y momentum here, it's mass times the y component of the velocity, but that y component of the velocity should be given a negative based on how we've set it up. And the mass is just, well, it's mass 1 and mass 2, right? It's one object now stuck together. So mass 1 plus mass 2 times v12 final times the sine of that angle C, right? For the x1, it's to the right, which we called positive x. So mass 1 plus mass 2 times the x component of its final velocity, which we found to be the final velocity times the cosine of that angle C. So v12 final times the cosine of the angle C. And there we go. So what's the total? I mean, there's only one object after, right? So it's just this expression again. That's the total final momentum. And same. Only one thing to add up to get the total, right? Because there's only one object. And so whatever the total x momentum of these were, right, when we added the x momentum of this to the x momentum of this, we know we have to get whatever this thing's x momentum is, right? Two objects became one, but the momentum is still conserved. So in this case, right, there was still some y momentum left over. Means mass 1 must have had larger y momentum than mass 2, right? Because overall the momentum in the system afterwards is downward. That means initially overall the momentum in the y-axis was downwards, right? So this must have had a larger magnitude than this, giving us an overall downward y momentum that was preserved, okay? So again, whatever these are, they will be the same numerically as those. Okay. Oh boy, look at this one. Two objects before, each with an x and y component to their momentum, and two objects after, each also with an x and y component to their momentum. So this is about the longest type you can get, where you have two things before and two things after, and both of them have components in both axes, both before and after, right? So it's not necessarily harder. It's the same stuff. It's just more of the same stuff. But it's not any more difficult. You just have to do more of it. All right, let's split all of these into their components, okay? And there we go, right? It's the same thing. Down and to the right, so the x component is to the right, the y component is down. Up and to the right, so the y component is up, the x component is to the right, right? And then it's just trigonometry to get those x and y components. So if you need to pause and look at these for a little bit if you're not quite sure how I got those, right? But it's the same process we've been using over and over again. So now that we've got all those x and y components, right, how do we get the momentum? We've got the x and y components of the velocity. So to get the x and y components of the momentum, we need to multiply velocities by masses, right? P equals mv. So let's just do that for all of these, being very careful. We've got lots of ups and downs, so we're going to really, need to be on our toes for remembering negatives. Normally, what we would probably do is once we got this y component, we just put the negative in right away so we don't forget, okay? But here we don't actually have numbers. So let's go ahead and fill in our table. I'm going to go ahead and do it all here. And there we go, right? Just same process, right? What is the total initial x momentum? Well, add the x momentum of mass 1 to the x momentum of mass 2. right? What's the total initial y momentum? Same thing, but with the y components, right? Just being careful about signs getting opposite directions. And the whole point here, right, is that whatever this is will be the same as this, right? So adding these up will be the same as adding those up. Adding these up will be the same as adding these up. And that's how we write our conservation of momentum equation that allows us to solve for anything we don't know, right? So there we go, okay? Same process as always. Split into the x and y components and then apply conservation of momentum in each axis separately. All right, last one here, okay? Taking a look at this, ooh, this is always nice. When the initial momentum of the whole system is 0, we've got a bomb here that's going to explode, so its initial momentum is 0. Later, it's going to explode into 3 parts, right? But if initially the object's overall velocity is 0, that means its x velocity is 0, and therefore its x momentum is 0, right? And same goes for the y-axis. It's not moving vertically if it's not moving at all. So initially our total momentum is 0 in the x-axis and 0 in the y-axis, right? Now finally, what do we know will be the total momentum in the x-axis? It'll be 0, right? Now, it will be the result of adding 3 separate x momenta up, but they will add to 0 because it has to be the same as the initial, right? And same goes in the y-axis. So we'll get an expression for those, but we know that adding those 3 x momenta up will equal 0, and adding those 3 y momenta up will equal 0. So let's just figure out what those have to add to. Or rather, what we are adding that will add to 0, okay? Well, looking here, I mean, 3 objects, 3 different velocities, each one having an x and a y component, right? They're both moving in both axes. So this one is kind of uppy-righty, so its y component is uppy, right? There's v1 final y, and its x component is righty to give us an overall up and to the right final velocity. So v1 final x looks like that, okay? And so we can see here using our trigonometry that, okay, now this is opposite, right? Be careful. Sometimes students think x is always going to be cos. It often is, just because naturally this is how it feels good to draw angles, but there's nothing wrong with giving the angle from the vertical, and that makes this the component that's actually opposite to our angle A, right? So in this case, the sine of the angle A would equal the x component of object 1's final velocity over object 1's final velocity, right? And therefore the x component is going to be v1 final times the sine of whatever angle A is, right? Same thing for the y-axis, except the y-axis is adjacent, so we'll use cos. And there we go. There are the x and y components of fragment 1's final velocity, which can, of course, then be used to find the x and y components of fragment 1's final momentum, right? We've just got to multiply those by the mass. Now, got to be careful here, right? We've got positive and negative momenta in both the x and the y axes. We kind of knew that would have to be true because we can see they all have x and y momentum, but we know we didn't start with any. So for every positive x momentum, there needs to be a negative x momentum to cancel it out. And for every positive y momentum, there needs to be some negative y momenta that add together to cancel it out, right? So what is mass 1's final x momentum? It's its mass times its final horizontal or x velocity, right? What's its final y momentum? It's its mass times its final y velocity. Those happen to both be in our positive direction, so we wouldn't slap a negative in there, right? Okay, let's repeat that process for these two. Here we go. Fragments 2 and 3's final components of their velocity look something like this, right? Down and to the left, so x component to the left, y component down. We'll make both of those negative when we actually do the math, right? And then here, down and to the right, so x component to the right, y component down. We'll make that y component negative when we actually do the math. So to get the momenta, what would we do? Multiply those masses by those velocities. So here we go. Just like that. Right? Sorry, I realized I forgot to use the sine A and cos A that we found, right? I just had it as V1 final X, but we figured out that V1 final X is just V1 final times the sine of A. So I just fixed those ones, right? And then added these ones in. Oops, I forgot something. Do you see something important I forgot? In mass 3, specifically its Y component, what did I forget? Downward, we were calling that negative, right? We need opposite directions to have opposite signs. These are vectors. They can cancel each other out. So mathematically, we make that happen by giving opposite directions, opposite signs. Okay, so what's the total final x momentum? I mean, we know it's 0, but that means these all add to 0, right? So 0 equals this plus this plus this, which would let us find an unknown velocity maybe, right? Or maybe an unknown mass. Who knows what's unknown? So add these, and we know we will get that will equal 0, right? And add these. And the fact that they equal 0 can figure out what anything we don't know has to be, right? Okay, so that wraps up Chapter 9, Lesson 3, and therefore wraps up Chapter 9, and therefore wraps up Unit A. So believe it or not, we are finished the first unit of Physics 30, okay? So you can now do, of course, like do your practice and ask your questions and all that stuff, right? But once you've done that and you're feeling good, you can do the Chapter 9B quiz, which covers conservation of momentum in both one axis and two axis. So one axis and two axes, okay? And then you can also actually book in a time for your Unit A exam. So there are multiple options given, okay, to make it work for however your schedule works out. And then you book a time, you'll join the Google Meet that's there, and you will write your supervised exam at your chosen time out of the options given. Okay, so make sure you book a time so I know when you're coming. If nobody books a time, then I don't open the Google Meet, and then sometimes students say, hey, I tried to write my test, but no one was there. And it's just because nobody told me they were coming, so I didn't bother opening the Google Meet that day or at that time. Okay, so yeah, there we go. That's Unit A. 1 unit down, 3 to go. That's the shortest unit for sure. Okay, but always feel free. Remember, reach out, ask questions, book a meeting. I'm always happy to help. And there we go. On to Unit B in the next lesson.